every star, every atom, every heartbeat, obeying rules we didn't write. For centuries, we thought the universe was chaos. But then, revelations struck like lightning. Newton uncovered the force that holds us down. Einstein shattered reality, revealing space and time as a single flowing fabric. Quantum physicists dove deeper and found strange, hidden laws beneath it all. So here's the haunting question. If these laws shape everything, who or what shaped them? And what happens if those laws ever change? The universe operates on a set of fundamental principles that govern everything from the smallest subatomic particles to the largest cosmic structures. These laws form the bedrock of our understanding of reality and shape the way the cosmos functions. At the core of these principles are the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, described by Einstein's theory of general relativity, is responsible for the large-scale structure of the universe, keeping planets in orbit and galaxies together. Electromagnetism governs the behavior of charged particles and is responsible for most of the phenomena we observe in daily life, from light to chemical reactions. The strong nuclear force binds quarks together to form protons and neutrons and holds atomic nuclei intact. The weak nuclear force is responsible for certain types of radioactive decay and plays a crucial role in stellar nucleosynthesis, the process by which stars create heavier elements. These forces work in concert with other fundamental laws, such as the conservation of energy and momentum, and the principles of quantum mechanics, which describe the behavior of matter and energy at the smallest scales. Together, these laws create the intricate tapestry of the universe we observe, from the dance of subatomic particles to the majestic swirl of galaxies across the cosmic expanse. In physics, a law is a fundamental principle that describes the behavior of the universe with remarkable consistency and accuracy. These laws are derived from extensive observations and experiments, standing the test of time and rigorous scientific scrutiny. Unlike theories, which attempt to explain why phenomena occur, laws focus on describing what happens under specific conditions. Physical laws are typically expressed as mathematical equations that relate different quantities or properties. However, the essence of these laws can often be conveyed in simple, straightforward terms. For instance, Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion unless acted upon by an external force. Scientists consider a principle to be a law when it has been repeatedly confirmed through observation and experimentation, with no known exceptions. These laws form the bedrock of our understanding of the physical world, allowing us to make precise predictions about how systems will behave under various circumstances. It is important to note that while laws are considered highly reliable, they are not absolute truths. As our understanding of the universe deepens, laws may be refined or even replaced by more comprehensive explanations. The pursuit of these fundamental principles drives scientific progress, constantly pushing the boundaries of our knowledge about the cosmos. Humans have been recognizing patterns in nature since the dawn of our species. Our early ancestors, living as hunter-gatherers, relied on their ability to spot patterns for survival. They observed animal migration patterns to predict the best hunting times and locations. They noticed seasonal changes in plants, helping them gather food more efficiently. This pattern recognition extended to the sky as well. Ancient civilizations tracked the movements of celestial bodies, noting the cycles of the moon and the positions of stars. This allowed them to create calendars, crucial for agricultural planning and religious ceremonies. The ancient Egyptians, for example, used the annual flooding of the Nile River to determine their agricultural cycle. As human societies developed, this innate ability to recognize patterns became more sophisticated. Early mathematicians and philosophers began to codify these observations, laying the groundwork for scientific inquiry. The ancient Greeks, for instance, sought to explain natural phenomena through logical reasoning, often based on observed patterns. The human brain is wired to seek out patterns, a trait that has been crucial to our survival and advancement as a species. This fundamental skill has driven scientific discovery, technological innovation, and our understanding of the universe around us. From the simplest observations of day and night to the complex algorithms used in modern science, pattern recognition remains a cornerstone of human cognition and scientific progress. Our understanding of universal laws has undergone remarkable transformations throughout history. Ancient civilizations observed patterns in the night sky, developing early models of celestial mechanics. These observations laid the groundwork for more sophisticated theories in later centuries. The scientific revolution marked a significant leap forward. Isaac Newton formulated his laws of motion and universal gravitation, providing a unified explanation for both earthly and celestial phenomena. This breakthrough allowed scientists to predict planetary motions with unprecedented accuracy, cementing the idea that the universe operates according to consistent, knowable laws. The 20th century brought further upheaval to our understanding. Albert Einstein's theories of special and general relativity revolutionized our concepts of space, time, and gravity. Quantum mechanics emerged, revealing the strange behavior of matter and energy at the smallest scales. These developments showed that the universe is far more complex and counterintuitive than previously thought. Today, scientists continue to refine and expand our knowledge of universal laws. The search for a theory of everything, which would unite all fundamental forces and particles, remains an active area of research. As we probe deeper into the cosmos and delve further into the quantum realm, our understanding of the laws governing the universe continues to evolve, promising new insights and discoveries in the years to come. Mathematics serves as the universal language of physics, providing a precise and powerful tool for describing the fundamental laws that govern our cosmos. From the smallest subatomic particles to the largest structures in the universe, mathematical equations capture the essence of how nature behaves. At its core, mathematics allows scientists to express complex relationships and patterns in a concise, unambiguous form. For instance, Einstein's famous equation relating mass and energy elegantly encapsulates a profound truth about the nature of our universe in just a few symbols. This mathematical representation enables physicists to make predictions and test theories with remarkable accuracy. Moreover, mathematics reveals symmetries and conservation laws that might not be immediately apparent through observation alone. The conservation of energy, momentum, and charge, all fundamental principles in physics, are deeply rooted in mathematical concepts. These mathematical underpinnings often guide researchers towards new discoveries and deeper understanding of the cosmos. Perhaps most importantly, mathematics allows us to extrapolate beyond the limits of human perception and experience. It enables scientists to describe phenomena at the quantum scale, model the behavior of black holes, and even explore the possibility of multiple dimensions. In this way, mathematics acts as a bridge, connecting our limited human perspective to the vast and often counterintuitive reality of the universe. The nature of universal laws has long fascinated scientists and philosophers alike. While we often think of these laws as immutable constants governing the cosmos, recent research suggests a more nuanced picture. Current scientific understanding indicates that some fundamental constants might have changed slightly over the history of the universe. For instance, studies of light from distant quasars hint at potential variations in the fine structure constant, which governs the strength of electromagnetic interactions. Moreover, the laws we observe might be specific to our particular universe. The multiverse theory proposes the existence of multiple universes, each potentially governed by its own set of physical laws. In this framework, what we perceive as universal constants might be variables set at the birth of each universe. However, it is important to note that within our observable universe, The laws of physics appear remarkably consistent across vast distances and spanning billions of years. Any changes, if they exist, are likely to be extremely subtle and occur over enormous timescales. The apparent stability of these laws has allowed the universe to evolve and develop complex structures, including life as we know it. Universal laws and scientific theories are both crucial components of our understanding of the universe, but they serve different roles in the scientific process. Universal laws, also known as physical laws, are fundamental principles that describe the behavior of the natural world. These laws are considered to be true everywhere in the universe and under all circumstances. They are typically expressed as simple, concise statements or mathematical equations that have been extensively tested and consistently proven accurate. Scientific theories, on the other hand, are comprehensive explanations of natural phenomena based on a large body of evidence and observations. While theories are well supported by empirical data, they are subject to refinement or even replacement as new evidence emerges. Theories often incorporate multiple laws and provide a broader framework for understanding complex systems or processes in nature. One key difference is that universal laws describe what happens in nature, while scientific theories explain why and how these phenomena occur. For example, Newton's law of universal gravitation describes the force of attraction between objects, but it does not explain the underlying mechanism of gravity. In contrast, Einstein's theory of general relativity provides a comprehensive explanation of how gravity works by describing it as a curvature of spacetime. Another distinction is that universal laws are generally simpler and more limited in scope, while scientific theories are more complex and far-reaching. Laws often focus on specific relationships or behaviors, whereas theories can encompass entire fields of study and integrate multiple concepts. Both laws and theories are essential to scientific progress, working together to deepen our understanding of the cosmos and drive further exploration and discovery. Determinism is a fundamental concept in our understanding of the universe and its laws. At its core, determinism suggests that every event or state of affairs, including human decisions and actions, is the inevitable and necessary consequence of previous events and conditions. In the context of universal laws, this means that if we could know the precise location and momentum of every particle in the universe, we could theoretically predict the entire future with perfect accuracy. The idea of determinism is closely tied to the laws of physics, particularly classical mechanics. These laws describe how objects move and interact with each other based on forces acting upon them. According to deterministic principles, if we know the initial conditions of a system and all the forces acting on it, we can calculate its future state with certainty. However, the discovery of quantum mechanics in the 20th century has complicated our understanding of determinism. At the quantum level, particles behave in ways that seem to defy classical determinism, introducing an element of probability and uncertainty. This has led to ongoing debates about whether the universe is truly deterministic or if there is an inherent randomness at its most fundamental level. Despite these quantum considerations, many scientists still view the universe as largely deterministic on macroscopic scales. The predictability of planetary orbits, chemical reactions, and many other phenomena supports this view. Ultimately, the concept of determinism challenges our notions of free will and the nature of causality, prompting us to reconsider our place in a universe governed by immutable laws. Universal constants are fundamental pillars of physics, serving as unchanging values that govern the behavior of the cosmos. These constants, such as the speed of light, gravitational constant, and Planck's constant, provide a consistent framework for understanding the universe across vast scales of space and time. The speed of light, for instance, acts as a cosmic speed limit, influencing our understanding of space, time, and the nature of reality itself. It plays a crucial role in Einstein's theory of relativity, shaping our comprehension of the universe's structure and evolution. The gravitational constant, on the other hand, determines the strength of gravity, affecting everything from the orbits of planets to the formation of galaxies. These constants are not just arbitrary numbers. They are precisely tuned values that allow the universe to exist as we know it. These constants are not just arbitrary numbers. They are precisely tuned values that allow the universe to exist as we know it. Even slight variations in these constants could result in a drastically different cosmos, potentially one where stars, planets, and life could not form. This fine-tuning has led some scientists to ponder the possibility of a multiverse, where our universe is just one of many with different sets of constants. The study of universal constants continues to be a frontier of physics research. Scientists are constantly refining measurements of these values and exploring whether they truly remain constant across cosmic time and space. This ongoing investigation not only deepens our understanding of the universe, but also pushes the boundaries of our most fundamental theories about reality. Universal laws form the bedrock of our understanding of reality, providing a consistent framework that governs the behavior of everything in the cosmos. These fundamental principles, such as gravity, electromagnetism, and the laws of thermodynamics, apply uniformly across the entire universe, from the smallest subatomic particles to the largest galactic structures. Our ability to observe and comprehend these laws has revolutionized our view of the world around us. For instance, the law of gravity explains not only why objects fall to Earth, but also how planets orbit stars and how galaxies maintain their shape. This universality allows us to make predictions about distant celestial bodies and understand phenomena occurring light years away. The consistency of these laws across time and space instills confidence in our scientific models and theories. It enables us to develop technologies that rely on these principles, from smartphones utilizing electromagnetic waves to spacecraft harnessing gravitational forces for propulsion. Moreover, our grasp of universal laws has led to profound philosophical questions about the nature of reality, determinism, and our place in the cosmos. As we continue to explore the universe, these laws serve as a guide, helping us unravel its mysteries and pushing the boundaries of human knowledge. They remind us that despite the vast diversity and complexity of the cosmos, there exists an underlying order that connects all things, large and small, near and far. The origin of the laws of physics remains one of the most profound mysteries in science. These fundamental rules govern the behavior of matter and energy throughout the universe, yet their source eludes our complete understanding. Scientists have uncovered and described these laws through careful observation and experimentation, but explaining why they exist or where they come from is a challenge that pushes the boundaries of physics and philosophy. Some theorists propose that our universe's laws emerged from the conditions present at the moment of the Big Bang, suggesting they are a product of the universe's initial state. Others speculate about the existence of a multiverse, where different universes might have different sets of physical laws. In this scenario, our universe's particular set of laws could be seen as one possibility among many. However, this idea raises further questions about what determines the rules governing the multiverse itself. Another intriguing possibility is that the laws of physics are not fixed but have evolved over time as the universe expanded and cooled. This concept, while controversial, suggests that the fundamental constants and rules we observe today might be the result of a long cosmic evolution. As we continue to explore these questions, the search for the origin of physical laws remains a central pursuit in our quest to understand the nature of reality itself. The question of whether universal laws can exist without a creator touches on fundamental aspects of physics, philosophy, and cosmology. Many scientists argue that the laws of physics, such as gravity, electromagnetism, and the strong and weak nuclear forces, are inherent properties of the universe itself. These laws describe how matter and energy interact, and they appear to be consistent across the observable universe. Some theories suggest that our universe might be one of many in a vast multiverse, each with its own set of physical laws. In this scenario, the laws we observe could be a result of random variations, with our universe happening to have the right conditions for complexity and life to emerge. This concept does not necessarily require a conscious creator to establish these laws. However, the origin of these laws remains a subject of intense debate and research. Some argue that the apparent fine-tuning of physical constants, which allow for the existence of stable matter and complex structures, points to a deliberate design. Others contend that our universe's laws are the result of natural processes we have yet to fully understand. Ultimately, the question of whether universal laws can exist without a creator remains open. Current scientific understanding does not require a creator to explain the existence of physical laws, but it also cannot definitively rule out the possibility. As our knowledge of the cosmos expands, we may gain new insights into the nature and origin of these fundamental principles that govern our universe. The origin of natural laws has long fascinated philosophers and scientists alike. One prominent view is the Platonic perspective, which suggests that natural laws exist independently of the physical universe. According to this idea, these laws are eternal and unchanging, governing the cosmos from a realm beyond space and time. In contrast, the empiricist view holds that natural laws are human constructs derived from observations of the physical world. This perspective argues that we discover patterns in nature and formulate laws to describe them, rather than uncovering pre-existing universal truths. Another philosophical stance is the necessitarian view, which posits that the laws of nature are necessary and could not have been different. This perspective suggests that the fundamental structure of reality dictates these laws, leaving no room for alternative possibilities. Conversely, the contingency perspective proposes that natural laws are not fixed or predetermined. This view allows for the possibility that laws could have been different or may even change over time, challenging the notion of universal constants. The concept of a lawgiver does not directly fit into modern scientific thinking. Science operates on the principle of methodical observation, experimentation, and evidence-based conclusions, rather than relying on the idea of a supreme being or entity establishing universal rules. In scientific understanding, the laws of nature are not decreed or imposed by any conscious entity. Instead, they are descriptions of observed patterns and behaviors in the physical world. These laws, such as gravity or thermodynamics, are derived from repeated observations and rigorous testing. Scientists continually refine and sometimes even replace these laws as new evidence emerges. This adaptability is a fundamental aspect of the scientific method, allowing our understanding of the universe to evolve and improve over time. While some individuals might find philosophical or personal meaning in the idea of a cosmic lawgiver, science itself remains neutral on such matters, focusing solely on what can be observed, measured, and tested in the natural world. The anthropic principle is a thought-provoking concept in cosmology that addresses the apparent fine-tuning of universal laws and constants. It suggests that the observable universe must have properties that allow for the existence of observers like ourselves. In other words, if the universe were not capable of supporting intelligent life, we would not be here to observe it. This principle relates to universal laws in a fascinating way. The fundamental constants and laws of physics, such as the strength of gravity, the speed of light, and the properties of subatomic particles, seem to be precisely calibrated to allow for the formation of stars, planets, and ultimately, life. If these constants were even slightly different, the universe as we know it might not exist. Consider, for example, the delicate balance of forces that allow stars to form and sustain nuclear fusion. If gravity were a bit stronger or weaker, stars might burn out too quickly or fail to ignite at all. Similarly, the electromagnetic force must be just right for atoms to form stable structures. These precise conditions raise questions about why our universe appears so finely tuned for life. The anthropic principle does not provide a definitive explanation for this apparent fine-tuning, but it offers a framework for understanding our place in the cosmos. It reminds us that our very existence as observers may influence how we perceive and interpret the universe around us, highlighting the deep connections between life, consciousness, and the fundamental nature of reality. The uniformity of physical laws across the cosmos is a fundamental assumption in modern science, yet it remains an intriguing question whether these laws could vary in different regions of the universe. Current observations and theories strongly support the idea that the laws of physics are constant throughout the observable universe. However, some scientists speculate about the possibility of slight variations or even entirely different physical laws beyond our cosmic horizon. One concept that explores this idea is the multiverse theory, which suggests the existence of multiple universes, each potentially governed by its own set of physical laws. In this scenario, our universe might be just one of many, each with unique properties and constants. While this idea is fascinating, it remains highly speculative and currently lies beyond our ability to test or observe directly. Another perspective considers the possibility of physical laws evolving over time or varying across vast cosmic distances. Some theories propose that fundamental constants, such as the speed of light or the strength of gravity, might have changed slightly over billions of years. However, current observations have not detected any significant variations in these constants within the limits of our measurement capabilities. It is important to note that even if physical laws did vary in other parts of the universe, such differences would likely be subtle. Dramatic changes in fundamental physics would likely result in universes vastly different from our own, potentially incapable of supporting the complex structures and life forms we observe. For now, the consistency of physical laws remains a cornerstone of our understanding of the cosmos, allowing us to study and make predictions about distant regions of space and time. Throughout history, cultures and religions worldwide have offered diverse explanations for the origin of natural laws. Many ancient civilizations attributed these laws to the actions of gods or divine beings. For instance, in ancient Greek mythology, the Olympian gods were thought to govern various aspects of nature, with Zeus controlling the sky and weather, and Poseidon ruling the seas. In monotheistic religions such as Judaism, Christianity, and Islam, natural laws are often seen as the handiwork of a single, all-powerful creator. These traditions view the universe as operating according to divine principles established at the moment of creation. Some adherents of these faiths see scientific discoveries as revealing the intricate design of their deity. Eastern philosophies like Hinduism and Buddhism often perceive natural laws as part of an eternal cosmic order. In Hinduism, the concept of dharma encompasses the fundamental principles governing the universe, while Buddhism speaks of dharma as the ultimate truth and natural order of reality. These traditions often view natural laws as timeless and inherent to existence itself. Indigenous cultures frequently explain natural laws through ancestral wisdom and spiritual connections to the land. Many Native American tribes, for example, see natural phenomena as manifestations of spirit beings or ancestral forces, with humans playing a role in maintaining cosmic balance through rituals and respect for nature. These varied cultural perspectives highlight the human drive to understand and explain the fundamental workings of our universe. Causality plays a fundamental role in our understanding of universal laws. These laws describe the consistent patterns and relationships we observe in nature, governing everything from the motion of planets to the behavior of subatomic particles. At its core, causality is the principle that every effect has a cause, and this concept underpins many of our scientific theories and explanations. Universal laws, such as the laws of thermodynamics or gravitation, rely on causal relationships to explain how different aspects of the universe interact. For instance, the law of gravity describes how mass causes a gravitational force, which in turn affects the motion of objects. This causal chain allows us to predict and explain phenomena across vast cosmic scales. The existence of universal laws themselves can be seen as a consequence of causality. These laws emerge from the fundamental properties and interactions of matter and energy, creating a framework of cause and effect that extends throughout the cosmos. This consistency allows scientists to formulate theories and make predictions about the behavior of the universe. However, it is important to note that our understanding of causality becomes more complex at the quantum level, where events can appear to violate classical notions of cause and effect. This has led to ongoing debates about the nature of causality and its role in shaping the fundamental laws of the universe, pushing the boundaries of our scientific understanding and philosophical inquiries. The emergence of universal laws from chaos is a fascinating concept that challenges our understanding of the cosmos. In the early moments of the universe, conditions were incredibly hot and dense, with energy and matter existing in a state of pure chaos. Yet, from this tumultuous beginning, the fundamental laws of physics as we know them today began to take shape. As the universe expanded and cooled, distinct forces separated from what may have been a single unified force. Gravity, electromagnetism, and the strong and weak nuclear forces emerged, each governing different aspects of how matter and energy interact. This process of spontaneous symmetry breaking allowed for the creation of structure in the universe. The laws of thermodynamics, which describe the behavior of energy and matter, also appear to have emerged from the initial chaos. These laws govern everything from the formation of stars to the cooling of a cup of coffee. Similarly, the principles of quantum mechanics, which dictate the behavior of particles at the smallest scales, arose as the universe evolved. While it may seem counterintuitive, chaos itself can give rise to order through self-organization. Complex systems, whether in physics, biology, or even social structures, can spontaneously develop patterns and laws that govern their behavior. This emergence of order from chaos is a recurring theme in our universe, suggesting that the fundamental laws we observe may indeed have arisen spontaneously from the primordial disorder of the early cosmos. Quantum mechanics fundamentally reshapes our view of the universe at the smallest scales. Unlike the predictable, deterministic world we experience in our everyday lives, quantum physics reveals a realm of probability and uncertainty. At the quantum level, particles can exist in multiple states simultaneously, a phenomenon known as superposition. This challenges our classical notion of definite states and outcomes. Furthermore, quantum entanglement allows particles to be instantaneously connected across vast distances, seemingly defying the speed of light limits set by relativity. The observer effect in quantum mechanics suggests that the very act of measurement can influence the outcome of an experiment. This raises profound questions about the nature of reality and the role of consciousness in shaping our universe. It blurs the line between the observer and the observed, a concept alien to classical physics. These quantum phenomena force us to reconsider our understanding of causality, locality, and even the nature of existence itself. As we delve deeper into the quantum world, we find that the universal laws governing the cosmos may be far more complex and counterintuitive than we ever imagined. The Big Bang Theory is our best explanation for how the universe began. It proposes that the cosmos started as an incredibly hot, dense point about 14 billion years ago. In a fraction of a second, this point expanded explosively, growing from smaller than an atom to encompassing all of space. As the universe expanded and cooled, it allowed for the formation of the first subatomic particles, which eventually combined to form atoms. These atoms, primarily hydrogen and helium, spread throughout the expanding space, forming vast clouds that would later coalesce into the first stars and galaxies. The Big Bang Theory is supported by several key pieces of evidence. One is the cosmic microwave background radiation, a faint glow that permeates all of space. This radiation is the afterglow of the Big Bang, cooled over billions of years as the universe expanded. Another piece of evidence is the abundance of light elements in the universe, which matches predictions made by the theory. It is important to note that the Big Bang was not an explosion in space, but an expansion of space itself. The theory does not explain what caused the Big Bang or what came before it, but it provides a robust framework for understanding the evolution of the universe from its earliest moments to the present day. The laws of physics, as we know them today, are intimately connected to the Big Bang, the monumental event that marked the birth of our universe approximately 13.8 billion years ago. These fundamental principles govern the behavior of matter and energy, shaping the cosmos from its earliest moments to the present day. In the initial instance following the Big Bang, the universe was an incredibly hot and dense state, unlike anything we can observe or recreate today. Our current understanding of physics struggles to describe these extreme conditions as the known laws begin to break down at such high energies and densities. This limitation has led scientists to search for a unified theory that can explain how gravity interacts with the other fundamental forces at these extreme scales. As the universe expanded and cooled, the laws of physics as we understand them began to take shape. The fundamental forces of nature separated and particles formed, eventually leading to the creation of atoms, stars, and galaxies. The cosmic microwave background radiation, a faint glow permeating all of space, serves as evidence of this early stage of the universe and provides crucial information about the conditions present shortly after the Big Bang. The Big Bang theory itself relies on the principles of general relativity, quantum mechanics, and thermodynamics to explain the evolution of the universe. These laws allow scientists to model the expansion of space, the formation of cosmic structures, and the abundance of elements we observe today. By studying the Big Bang and its aftermath, researchers continue to refine our understanding of the fundamental laws that govern our universe, pushing the boundaries of human knowledge ever further. The laws of physics as we understand them today were not created at the moment of the Big Bang, but rather emerged as the universe expanded and cooled. In the earliest moments after the Big Bang, the extreme conditions of temperature and density were so intense that our current understanding of physics breaks down. As the universe expanded and temperatures dropped, the fundamental forces of nature began to separate and take on their distinct characteristics. Gravity separated first, followed by the strong nuclear force, and then the weak nuclear force and electromagnetism. This process, known as symmetry breaking, allowed the laws of physics to manifest as we observe them today. It is important to note that the laws of physics describe the behavior of the universe rather than prescribe it. They are our best mathematical models to explain the observed phenomena, refined through centuries of scientific inquiry and experimentation. These laws have remained consistent throughout the observable history of the universe, suggesting they are intrinsic to its nature. Current theories propose that the laws of physics might have been different in the extreme conditions immediately following the Big Bang. Some scientists even speculate about the existence of a multiverse where different universes might have different physical laws. However, these ideas remain in the realm of theoretical physics and are subjects of ongoing research and debate. Cosmic inflation is a theory that describes an incredibly rapid expansion of the early universe, occurring just a fraction of a second after the Big Bang. This brief but intense period of growth saw the universe expand faster than the speed of light, stretching from a subatomic scale to a cosmic expanse in an instant. This concept revolutionizes our understanding of universal laws by providing solutions to long-standing cosmological puzzles. It explains why the universe appears flat and uniform on large scales, resolving the horizon problem that questioned how distant regions of space could have similar properties without ever being in causal contact. Inflation also accounts for the origin of cosmic structure, suggesting that quantum fluctuations during this expansion became the seeds for galaxies and cosmic webs we observe today. Inflation challenges our intuitions about the nature of space and time. It suggests that the observable universe is just a tiny fraction of a much larger, possibly infinite cosmos. This idea forces us to reconsider the concept of the universe's beginning and raises questions about the potential existence of multiple universes or a multiverse. Moreover, cosmic inflation affects our understanding of fundamental physics. The extreme energies and rapid expansion during this period push the boundaries of known physics, requiring us to consider new particles, fields, and potentially undiscovered laws of nature to explain this phenomenon. As we continue to study cosmic inflation, we may uncover deeper truths about the fabric of reality and the origins of our universe. The question of what happened before the Big Bang is one of the most intriguing and challenging in cosmology. Our current understanding of the universe is limited by the Big Bang itself, which serves as a cosmic horizon beyond which we cannot directly observe or measure. The Big Bang theory describes the rapid expansion and evolution of the universe from an incredibly hot, dense state. However, it does not explain the origin of that initial state or what might have preceded it. Some scientists argue that asking what came before the Big Bang is meaningless, as time itself may have begun with the Big Bang. Nevertheless, theoretical physicists have proposed several speculative models to address this question. One idea suggests a cyclical universe that expands and contracts repeatedly, with our Big Bang being just one in an infinite series. Another concept, known as eternal inflation, posits that our universe is one of many bubble universes constantly forming in a larger multiverse. While these ideas are fascinating, they remain highly theoretical and currently beyond our ability to test or verify. As our understanding of physics and cosmology advances, we may develop new ways to probe the earliest moments of the universe and potentially gain insights into its ultimate origins. Scientists employ a variety of sophisticated techniques to study the early moments of the universe. One of the most powerful tools is the analysis of cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This ancient light provides a snapshot of the universe when it was only about 380,000 years old, offering crucial insights into its early composition and structure. Particle accelerators like the Large Hadron Collider also play a vital role in this research. By smashing particles together at incredibly high energies, scientists can recreate conditions similar to those that existed fractions of a second after the Big Bang. These experiments help us understand the behavior of matter and energy in the extreme conditions of the early universe. Computer simulations are another essential tool in cosmology. Using supercomputers, researchers can model the evolution of the universe from its earliest moments, testing theories against observational data. These simulations allow scientists to explore scenarios that are impossible to recreate in a laboratory, providing valuable insights into the processes that shaped our cosmos. Astronomers also study the oldest and most distant objects in the universe, such as ancient galaxies and quasars. By observing these cosmic relics, scientists can piece together the history of the universe, working backwards in time to understand its earliest epochs. Each of these methods contributes to our ever-growing understanding of the birth and evolution of the cosmos. The cosmic microwave background is the oldest light in the universe, a faint glow of radiation that fills all of space. This ancient light began its journey about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. This primordial radiation provides us with a snapshot of the early universe, offering crucial evidence that supports our understanding of cosmic evolution and the Big Bang theory. The cosmic microwave background is remarkably uniform in all directions, which tells us that the universe was once incredibly hot and dense and has been expanding and cooling ever since. The subtle variations in temperature we observe in the cosmic microwave background reveal the seeds of cosmic structure. These tiny fluctuations eventually grew into the galaxies and galaxy clusters we see today, guided by the force of gravity. This process demonstrates the universality of gravitational laws across cosmic scales and throughout the history of the universe. Furthermore, the precise characteristics of the cosmic microwave background align with predictions made by our current models of physics. This agreement between theory and observation reinforces our confidence in the fundamental laws that govern the cosmos, from the behavior of subatomic particles to the large-scale structure of the universe itself. Time, as we understand it, began with the Big Bang, the cosmic event that marked the birth of our universe. Before this moment, the concept of time as we know it did not exist. The Big Bang not only gave rise to matter and energy, but also to the fabric of space-time itself. In the context of universal laws, time plays a crucial role. The laws of physics, such as the conservation of energy and the second law of thermodynamics, are intrinsically linked to the passage of time. These laws govern how events unfold and how systems change over time, shaping the evolution of the universe from its earliest moments to the present day. Einstein's theory of relativity further illuminates the relationship between time and the universe. It reveals that time is not absolute, but relative, capable of being stretched or compressed depending on factors like gravity and velocity. This understanding has profound implications for our perception of cosmic events and the very nature of reality. As we peer deeper into the cosmos, we are essentially looking back in time. The light from distant galaxies takes billions of years to reach us, providing a window into the universe's past. This unique perspective allows scientists to study the evolution of cosmic structures and test theories about the universe's origins, all while grappling with the fundamental nature of time itself. Our current models of the early universe, while impressive, face several key limitations. One major challenge is the lack of direct observational evidence from the first moments after the Big Bang. The cosmic microwave background radiation, our earliest window into the universe, only shows us what happened about 380,000 years after the initial explosion. This leaves a significant gap in our understanding of the very earliest stages of cosmic evolution. Another limitation stems from the extreme conditions present in the early universe. The intense energies and densities of that era push our physics theories to their limits. Our current models struggle to reconcile quantum mechanics with general relativity, two fundamental pillars of modern physics that seem incompatible at the smallest scales and highest energies. This makes it difficult to accurately describe what happened during the first fractions of a second after the Big Bang. Furthermore, our models face challenges in explaining certain large-scale structures we observe today. The distribution of galaxies and the presence of supermassive black holes in the early universe are not fully accounted for by our current understanding. This suggests there may be aspects of cosmic evolution we have yet to uncover or fully comprehend. Lastly, the nature of dark matter and dark energy, which play crucial roles in the universe's structure and expansion, remains elusive. While our models incorporate these mysterious components, we still lack a fundamental understanding of what they are. This gap in knowledge limits our ability to fully describe the universe's early development and its subsequent evolution over billions of years. The concept of multiple Big Bangs is a fascinating area of speculation in cosmology. While our current understanding points to a single Big Bang as the origin of our observable universe, some theories propose the possibility of other universes beyond our own, each potentially arising from its own Big Bang event. One such idea is the concept of the multiverse, where our universe might be just one of many. In this scenario, each universe could have its own Big Bang, existing in parallel with others. These separate universes might have different physical laws, constants, or even dimensions. Another perspective comes from the theory of eternal inflation. This model suggests that the process of cosmic inflation, which caused our universe to rapidly expand in its earliest moments, might be ongoing in other regions of space. This could lead to the continuous creation of new universes, each sparked by its own Big Bang-like event. However, it is important to note that these ideas remain highly speculative. The concept of multiple Big Bangs or parallel universes lies at the frontier of theoretical physics and cosmology, and currently, we have no way to directly observe or test these hypotheses. Our scientific understanding continues to evolve, and future discoveries may shed more light on these intriguing possibilities. The multiverse theory proposes that our universe is not alone, but part of a vast collection of universes existing simultaneously. This concept challenges our traditional understanding of reality and expands our view of existence beyond the boundaries of our observable cosmos. According to this theory, there could be an infinite number of universes, each with its own set of physical laws, constants, and possibly even different versions of ourselves. These parallel universes might exist in different dimensions or branching timelines, separated from our own by barriers we cannot directly observe or interact with. Some scientists suggest that the multiverse could explain certain puzzling aspects of our universe, such as its seemingly fine-tuned properties that allow for the existence of life. In this view, our universe might be just one of countless possibilities, with the right conditions for life emerging by chance among the infinite variations. While the multiverse theory is intriguing, it remains highly speculative and controversial within the scientific community. Researchers continue to explore ways to test and potentially verify this concept, pushing the boundaries of our understanding of the cosmos and our place within it. The concept of multiple universes, often called the multiverse, profoundly challenges our understanding of universal laws. Our current scientific framework is built on the assumption that the laws of physics are constant and uniform throughout our observable universe. However, the multiverse theory suggests that other universes might exist with entirely different sets of physical laws. This idea forces us to reconsider what we mean by universal laws. If multiple universes exist, each with its own unique set of rules governing fundamental forces like gravity or electromagnetism, then our laws may not be truly universal after all. They might simply be local phenomena, applicable only to our particular universe. Furthermore, the multiverse concept raises questions about the fine-tuning of our universe. Many physicists have noted that the fundamental constants in our universe seem precisely calibrated to allow for the existence of complex structures like galaxies, stars, and life. In a multiverse scenario, our universe could be just one of countless versions, each with different physical constants. This would explain the apparent fine-tuning without requiring a guiding hand or special significance for our particular set of laws. The multiverse theory also impacts our understanding of causality and the origins of our universe. If multiple universes exist, they might interact or give birth to new universes, challenging our notions of a single, definitive beginning to everything. This forces us to expand our thinking beyond the confines of our observable universe and consider a much grander, more complex cosmic landscape. The possibility of different universes with varying laws of physics is a fascinating concept in modern cosmology. This idea stems from theories like the multiverse, which suggests the existence of multiple universes beyond our own. In these hypothetical realms, the fundamental constants and laws that govern reality could differ from what we observe in our universe. Our understanding of physics is based on observations within our own universe, but theoretical physicists speculate that other universes might operate under completely different rules. For instance, the strength of gravity, the speed of light, or even the behavior of subatomic particles could be drastically different in another universe. These differences could lead to universes with wildly different properties. Some might collapse instantly, while others could expand too rapidly for stars and galaxies to form. In some universes, complex structures like atoms might never come into existence, making life as we know it impossible. The idea of varying physical laws across universes raises profound questions about the nature of reality and our place within it. It challenges us to consider whether our universe, with its seemingly fine-tuned constants that allow for our existence, is unique or just one of countless possibilities in a vast cosmic landscape. The fine-tuning argument is a concept in cosmology that points to the precise conditions necessary for life in our universe. It suggests that the fundamental constants and laws of physics appear to be delicately balanced, allowing for the existence of stable matter, stars, and ultimately life as we know it. Even small changes to these constants could result in a universe inhospitable to life. This apparent fine-tuning has led some to propose that our universe might be intentionally designed. However, the multiverse theory offers an alternative explanation. This theory suggests that our universe is just one of many, possibly infinite, universes with varying physical laws and constants. In the context of the multiverse, our universe's seemingly perfect conditions for life become less improbable. If there are countless universes with different properties, it's not surprising that at least one would have the right conditions for life to emerge. We simply happen to exist in such a universe because it's the only one where we could exist. The multiverse theory thus provides a naturalistic explanation for fine-tuning without resorting to design. It suggests that rather than our universe being uniquely tailored for life, we are the product of a vast cosmic lottery where life emerges in those universes with suitable conditions. This connection between fine-tuning and the multiverse remains a topic of intense scientific and philosophical debate. String theory and M-theory offer intriguing perspectives on the concept of a multiverse, expanding our understanding of the cosmos beyond the boundaries of our observable universe. These theories suggest that our universe might be just one of many, existing within a vast cosmic landscape. At their core, string theory and M-theory propose that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. These strings can vibrate in different ways, giving rise to the particles and forces we observe. However, for these theories to work mathematically, they require the existence of extra dimensions beyond the four we experience in everyday life. This is where the multiverse concept comes into play. According to these theories, our universe could be a three-dimensional membrane, or brain, floating in a higher dimensional space. Other brains might exist in this space, each representing a different universe with its own physical laws and constants. These parallel universes could be separated from ours by the extra dimensions, explaining why we cannot directly observe or interact with them. Furthermore, string theory and M-theory suggest that there could be an enormous number of possible vacuum states, each corresponding to a universe with different properties. This vast landscape of potential universes, combined with the idea of cosmic inflation, supports the notion that multiple universes could have formed, each with its own unique characteristics. This theoretical framework provides a compelling explanation for why our universe appears finely tuned for life, as it suggests we simply exist in one of the many universes where conditions happen to be right for our existence. The multiverse theory, while captivating, remains a topic of intense debate in the scientific community. Several lines of evidence lend support to this intriguing concept, though it is important to note that none are conclusive. One piece of evidence comes from quantum mechanics, specifically the many worlds interpretation. This suggests that every possible outcome of a quantum event occurs in a separate universe, potentially creating an infinite number of parallel realities. While this interpretation aligns with mathematical models, it has not been directly observed or proven. Cosmic inflation theory provides another tantalizing clue. This widely accepted model of the early universe proposes that space expanded rapidly just after the Big Bang. Some versions of this theory suggest that inflation might be eternal, constantly creating new universes in a vast cosmic landscape. This could explain why our universe appears fine-tuned for life, as it would be one of countless universes with varying physical laws. String theory, a candidate for a unified theory of physics, also hints at the possibility of multiple universes. It proposes the existence of extra dimensions which could harbor other universes with different properties. However, string theory remains unproven and lacks experimental evidence. As scientists continue to explore these ideas, the concept of a multiverse remains a fascinating frontier in cosmology. The multiverse theory challenges our traditional understanding of universal laws and their origins. This concept suggests that our universe might be just one of many, each potentially governed by its own set of physical laws and constants. In this framework, what we perceive as universal laws might only be applicable to our particular universe. This theory proposes that during the process of cosmic inflation, numerous bubble universes could have formed, each with slightly different initial conditions. These varying conditions might have led to the development of diverse physical laws across different universes. These varying conditions might have led to the development of diverse physical laws across different universes. As a result, the constants and laws we observe in our universe, such as the strength of gravity or the speed of light, might not be universal across all realities. The multiverse theory also introduces the idea of fine-tuning. It suggests that our universe's laws and constants are precisely calibrated to allow for the existence of complex structures, including life. In a multiverse scenario, this fine-tuning could be explained by the sheer number of universes with different properties, making it more likely that at least one would have the right conditions for life to emerge. However, it is important to note that the multiverse theory remains highly speculative and currently lacks direct observational evidence. While it offers intriguing possibilities for explaining the nature of our universe's laws, it also raises new questions about the fundamental nature of reality and the limits of scientific inquiry. The multiverse theory challenges our fundamental understanding of reality and existence. It suggests that our universe is just one of many, perhaps even an infinite number, existing simultaneously. This concept has profound implications for how we view our place in the cosmos and the nature of reality itself. One key philosophical question raised by the multiverse theory is the issue of uniqueness and significance. If there are countless universes, each with its own set of physical laws and conditions, our existence might seem less special or meaningful. However, it could also be argued that the sheer vastness and diversity of the multiverse make our particular existence even more remarkable. The multiverse theory also impacts our understanding of causality and free will. In some interpretations, every possible outcome of every decision occurs in different universes. This raises questions about the nature of choice and whether our actions truly matter if all possibilities are realized somewhere in the multiverse. Furthermore, the concept of multiple universes challenges our notions of creation and purpose. It may require us to reconsider traditional ideas about the origin of the universe and our role within it. The multiverse theory invites us to contemplate the possibility of realities far beyond our current comprehension, pushing the boundaries of philosophical and scientific thought. The multiverse theory and the anthropic principle are interconnected concepts that offer intriguing perspectives on our existence in the cosmos. The multiverse theory proposes that our universe is just one of many, possibly infinite, universes existing simultaneously. Each of these universes might have different fundamental constants, laws of physics, and initial conditions. The anthropic principle, on the other hand, suggests that the observable properties of our universe are compatible with the conscious life that observes it. In other words, we find ourselves in a universe that allows for our existence, because if it did not, we would not be here to observe it. When we combine these ideas, the multiverse theory provides a framework that can explain the apparent fine-tuning of our universe without resorting to supernatural explanations. If there are countless universes with varying properties, it becomes statistically likely that at least one of them would have the right conditions for life to emerge. We happen to find ourselves in such a universe because it is the only type where we could exist. This connection between the multiverse and the anthropic principle offers a potential solution to the question of why our universe seems so perfectly suited for life. Rather than being the result of design or extreme coincidence, our life-supporting universe could be one of many possibilities within a vast multiverse, with observers like us inevitably arising in those universes, capable of supporting life. The concept of multiple universes, often called the multiverse, is a fascinating idea that has captivated scientists and philosophers alike. While our observable universe is vast, containing hundreds of billions of galaxies, some theories suggest it might be just one of countless others. One prominent idea comes from inflationary theory, which proposes that our universe underwent a period of rapid expansion shortly after the Big Bang. This theory also suggests that this process of inflation might be eternal, constantly creating new bubble universes, each with its own physical laws and properties. Another perspective arises from quantum mechanics, which describes the behavior of particles at the smallest scales. Some interpretations of quantum theory propose that every possible outcome of a quantum event occurs, each in its own separate universe. This could lead to an infinite number of parallel universes, differing from ours in ways both subtle and dramatic. However, it is crucial to note that while these ideas are intriguing and based on established scientific principles, they remain theoretical. The existence of other universes, if they exist, lies beyond our current ability to observe or test directly. Scientists continue to explore these concepts, seeking ways to gather evidence that might support or refute the idea of a multiverse. Our consciousness profoundly shapes how we perceive and interpret the laws governing the universe. The human mind, with its unique ability to process complex information and form abstract concepts, allows us to grasp and articulate the fundamental principles that underpin reality. Our conscious experience of time, for instance, influences our understanding of causality and the arrow of time in physics. We perceive events as occurring in a linear sequence, which aligns with our everyday experiences, but may not fully capture the true nature of time as described by theories like relativity. Moreover, our consciousness enables us to develop and comprehend mathematical models that describe universal laws. These models, while powerful tools for prediction and explanation, are ultimately human constructs filtered through our cognitive abilities and limitations. This raises intriguing questions about whether the universe truly operates according to these laws or if they are simply the best approximations our minds can create. Interestingly, the very act of conscious observation plays a role in quantum mechanics, where the observer effect suggests that the act of measurement can influence the behavior of subatomic particles. This phenomenon highlights the complex relationship between human consciousness and the fundamental nature of reality, blurring the line between the observer and the observed in ways that continue to challenge our understanding of the universe. The observer effect in quantum mechanics reveals a fundamental and perplexing aspect of our universe at its smallest scales. This phenomenon describes how the very act of observing or measuring a quantum system can change its behavior or properties. Unlike in classical physics, where observation is assumed to have no impact on the system being studied, quantum mechanics introduces a level of uncertainty and interaction between the observer and the observed. At the quantum level, particles exist in a state of superposition, meaning they can potentially be in multiple states simultaneously. However, when we attempt to measure or observe these particles, this superposition collapses into a single, definite state. This collapse is not due to any physical interaction with our measuring devices, but rather it is an inherent feature of quantum systems. The implications of the observer effect are profound and counterintuitive. It suggests that reality at the quantum scale is not fixed or predetermined, but rather it is influenced by the act of measurement itself. This challenges our classical notions of objectivity and raises questions about the nature of reality and our role in shaping it. The observer effect has been demonstrated in numerous experiments, including the famous double-slit experiment. In this experiment, particles behave differently depending on whether they are being observed or not, showing wave-like or particle-like properties accordingly. This effect continues to puzzle scientists and philosophers alike, highlighting the mysterious and often counterintuitive nature of the quantum world. The relationship between consciousness and the fundamental laws of the universe is a profound and perplexing question that has intrigued scientists and philosophers for centuries. While our current understanding of physics does not require consciousness to explain the workings of the cosmos, some theories propose intriguing connections. One perspective suggests that consciousness might be an intrinsic property of the universe, similar to mass or charge. This idea, known as panpsychism, posits that all matter has some form of consciousness. If true, it could imply that consciousness plays a role in shaping reality at a fundamental level. Quantum mechanics, with its emphasis on observation affecting outcomes, has led some to speculate about the role of consciousness in collapsing wave functions. However, most physicists interpret this as a measurement issue rather than evidence of consciousness influencing reality. Some researchers explore the idea that consciousness might be involved in the fine-tuning of universal constants. They argue that the precise values of these constants, which allow for the existence of complex structures like stars and life, could be influenced by a cosmic consciousness. However, this remains highly speculative and lacks empirical evidence. Quantum mechanics and consciousness intersect in fascinating ways, sparking debate among physicists and philosophers alike. The Copenhagen interpretation, one of the most widely accepted views of quantum mechanics, suggests that consciousness plays a role in collapsing the wave function, essentially bringing quantum possibilities into concrete reality through observation. This idea has led some to speculate that consciousness itself might have quantum properties. The many worlds interpretation offers a different perspective. It proposes that all possible outcomes of quantum measurements occur, but in separate, branching universes. In this view, consciousness does not cause wave function collapse, but instead becomes entangled with particular measurement outcomes in different branches of reality. Some researchers have explored the possibility that quantum processes in the brain, such as those occurring in microtubules within neurons, could be the basis of consciousness. This quantum brain hypothesis suggests that consciousness emerges from quantum coherence in neural structures, potentially explaining phenomena like free will and subjective experience. Critics of quantum consciousness theories argue that the brain is too warm and wet for quantum effects to play a significant role in cognition. They contend that classical physics adequately explains brain function and that invoking quantum mechanics unnecessarily complicates our understanding of consciousness. The debate continues, highlighting the complex relationship between the quantum world and our conscious experience. Consciousness remains one of the most perplexing mysteries in science. The hard problem of consciousness refers to the challenge of explaining how subjective, first-person experiences arise from physical processes in the brain. While we can observe neural activity and correlate it with reported conscious experiences, we struggle to explain why we have inner subjective experiences at all. This dilemma relates to universal laws in intriguing ways. Some scientists propose that consciousness may be a fundamental feature of the universe, similar to other basic physical properties. Just as electromagnetism and gravity are woven into the fabric of reality, consciousness might be an intrinsic aspect of the cosmos. This perspective suggests that the laws governing consciousness could be as fundamental as those describing matter and energy. Others argue that consciousness emerges from complex information processing, and that the right set of physical laws and initial conditions in our universe allowed for the evolution of conscious systems. In this view, consciousness is not fundamental, but arises from particular arrangements of matter and energy that follow universal laws. The hard problem of consciousness challenges our understanding of reality and pushes us to reconsider the nature of physical laws. It raises profound questions about the relationship between mind and matter, and whether our current scientific framework is sufficient to fully explain the phenomenon of conscious experience. As we continue to explore this frontier, we may need to expand or revise our conception of universal laws to accommodate the puzzle of consciousness. The concept of free will in a universe governed by physical laws presents a fascinating paradox. On one hand, we have the deterministic nature of the cosmos, where every action and reaction follows precise, predictable patterns dictated by the fundamental forces of nature. These laws, from gravity to electromagnetism, shape the behavior of everything from subatomic particles to galactic superclusters. Yet, humans have long held the notion of free will, the ability to make conscious decisions and shape our own destinies. This seeming contradiction has puzzled philosophers and scientists for centuries. Some argue that free will is merely an illusion, a byproduct of our complex neural processes that give us the sensation of choice while our actions are predetermined by the physical state of our brains and the universe around us. Others propose that quantum mechanics, with its inherent uncertainty and probabilistic nature, might provide a loophole for free will. At the quantum level, particles exhibit behavior that appears random and unpredictable, potentially allowing for genuine choice to emerge from the fabric of reality. However, it remains unclear how these quantum effects could translate to the macroscopic scale of human decision-making. Ultimately, the question of free will in a law-governed universe touches on deep issues of consciousness, determinism, and the nature of reality itself. As our understanding of the brain and the fundamental workings of the cosmos continues to evolve, we may gain new insights into this age-old dilemma, potentially reshaping our view of ourselves and our place in the universe. The emergence of consciousness remains one of the most profound mysteries in science. Universal laws, particularly those governing physics and chemistry, offer tantalizing clues but have yet to provide a complete explanation for how consciousness arises. Quantum mechanics, a fundamental theory describing nature at the smallest scales, suggests that consciousness might be linked to the quantum properties of our brains. Some scientists propose that quantum effects in neural microtubules could give rise to conscious experiences. However, this idea remains highly speculative and controversial within the scientific community. Information theory presents another avenue for exploring consciousness. It posits that consciousness might emerge from the integration and processing of information in complex systems like the brain. This approach aligns with observations of how our brains create unified experiences from disparate sensory inputs. While universal laws have not yet fully explained consciousness, they provide a framework for ongoing research. As our understanding of the brain and fundamental physics deepens, we may uncover new connections between universal principles and the emergence of conscious awareness. The quest to solve this enigma continues to drive scientific inquiry and philosophical debate. Panpsychism is a philosophical concept proposing that consciousness or mind is a fundamental feature of the physical world, present in all matter to some degree. This view suggests that even the smallest particles in the universe possess a form of subjective experience or inner life, albeit in a very rudimentary form. Relating panpsychism to universal laws offers an intriguing perspective on the nature of reality. Just as gravity and electromagnetism are fundamental forces that apply throughout the cosmos, panpsychism posits consciousness as an equally ubiquitous property. This idea challenges the conventional notion that consciousness emerges solely from complex biological systems like brains. Some proponents argue that panpsychism could help bridge the explanatory gap between physical processes and subjective experience, a problem that has long puzzled philosophers and scientists. By viewing consciousness as an intrinsic aspect of matter, panpsychism suggests a universe where mind and matter are deeply interconnected rather than separate realms. However, it is important to note that panpsychism remains a controversial and debated concept in both philosophy and science. While it offers a unique approach to understanding consciousness and its place in the universe, many researchers remain skeptical of its validity and explanatory power. Altered states of consciousness profoundly impact our perception of reality and its fundamental laws. These states, which can be induced through various means such as meditation, psychedelic substances, or even extreme physical conditions, often lead to a dramatic shift in how we experience and interpret the world around us. During altered states, our normal sensory processing and cognitive functions are disrupted. This disruption can result in experiences that seem to defy our understanding of physical laws. For instance, individuals might report a distorted sense of time, where minutes feel like hours or vice versa. Spatial perception can also be affected, with objects appearing to change size or distance in impossible ways. Moreover, altered states can blur the boundaries between self and environment, leading to experiences of unity or oneness with the universe. This phenomenon challenges our usual perception of separate, individual consciousness. Some individuals report accessing what they believe to be higher dimensions or alternate realities, experiences that are difficult to reconcile with our everyday understanding of the physical world. These altered perceptions raise intriguing questions about the nature of reality itself. Are our normal waking states providing us with an accurate representation of the universe, or are altered states revealing aspects of reality that we usually cannot perceive? While science cannot yet fully explain these experiences, they continue to fascinate researchers and philosophers alike, pushing the boundaries of our understanding of consciousness and reality. The idea that universal laws could be a product of collective consciousness is a fascinating concept that bridges the realms of physics and philosophy. This notion suggests that the fundamental rules governing our universe might not be fixed, external constraints, but rather emergent properties arising from the combined mental processes of all conscious entities. While this idea may seem far-fetched at first glance, it aligns with some interpretations of quantum mechanics, which propose that consciousness plays a role in shaping reality. The observer effect, for instance, suggests that the act of observation can influence the behavior of quantum systems. Extending this concept to a universal scale, one could speculate that the collective observations and thoughts of all conscious beings might shape the very fabric of reality. However, it is important to note that this idea remains highly speculative and lacks empirical evidence. Most physicists and cosmologists maintain that the laws of nature are inherent properties of the universe, existing independently of conscious observation. These laws appear to be consistent across vast cosmic distances and throughout the observable history of the universe, which argues against them being products of localized consciousness. Nonetheless, the relationship between consciousness and the fundamental nature of reality remains an open question in both science and philosophy. As our understanding of the universe and consciousness evolves, we may gain new insights into this intriguing possibility, potentially reshaping our perception of the cosmos and our place within it. The simulation hypothesis proposes that our reality, including the entire universe and our consciousness, might be an advanced computer simulation created by a highly sophisticated civilization. This mind-bending concept suggests that everything we experience, from the ground beneath our feet to the stars in the sky, could be part of an incredibly complex virtual reality. Proponents of this hypothesis argue that as technology advances, our ability to create realistic simulations improves. They reason that if a civilization reaches a point where they can simulate entire universes, they would likely create many such simulations. Statistically, this means there could be countless simulated realities and only one base reality, making it more probable that we exist within a simulation than in the original, non-simulated universe. The implications of this hypothesis are profound, challenging our understanding of reality, consciousness, and the nature of existence itself. It raises questions about the purpose of such a simulation and the nature of the beings who might have created it. Some even speculate that our universe could be a simulation within a simulation, creating a potentially infinite regression of realities. Critics of the simulation hypothesis point out that it is currently unfalsifiable, meaning we have no way to prove or disprove it conclusively. They also argue that the computational power required to simulate an entire universe down to the quantum level would be unimaginably vast, potentially exceeding the resources available in the physical universe. The simulation hypothesis proposes that our reality, including the universe and its fundamental laws, might be an advanced computer simulation created by a more sophisticated civilization. This concept intersects with questions about the origin of universal laws in intriguing ways. If we consider the possibility that our universe is simulated, it suggests that the laws of physics, chemistry, and other fundamental principles could be programmed parameters rather than inherent properties of a base reality. In this scenario, the origin of universal laws would be rooted in the decisions and designs of the simulators, who would have established these rules to govern the behavior of their created universe. This perspective challenges traditional views on the nature of physical laws. Instead of emerging from some underlying cosmic principle, these laws could be seen as carefully crafted rules designed to create a stable and consistent simulated environment. The fine-tuning of universal constants, which has long puzzled scientists, might be explained as intentional adjustments made by the creators of the simulation to produce a universe capable of supporting complexity and life. However, it is crucial to note that the simulation hypothesis remains a philosophical and speculative idea, not a scientifically proven concept. It raises profound questions about the nature of reality and our place within it, but does not provide definitive answers about the true origin of universal laws. Scientists continue to explore and study the fundamental principles of our universe, seeking to understand their origins through observation, experimentation, and theoretical work, regardless of whether our reality is base or simulated. The idea that our universe might be a computer simulation is a fascinating concept that has intrigued scientists, philosophers, and science fiction enthusiasts alike. This notion, often referred to as the simulation hypothesis, suggests that our reality could be an artificial construct created by an advanced civilization or beings with immense computational power. While it may sound like pure science fiction, some respected physicists and philosophers have seriously considered this possibility. They argue that as our own computing capabilities advance, we are becoming increasingly able to create complex simulations of reality. If this trend continues, it is conceivable that a civilization far more advanced than ours could create a simulation so sophisticated that it would be indistinguishable from what we perceive as reality. However, it is important to note that there is currently no scientific evidence to support the simulation hypothesis. The idea remains purely speculative and faces numerous challenges. For instance, simulating an entire universe down to the quantum level would require an unimaginable amount of computing power, far beyond anything we can currently conceive. Critics of the simulation hypothesis also point out that it raises more questions than it answers. If we are in a simulation, who created it and why? And if they could create our universe, what kind of reality do they inhabit? Despite these challenges, the simulation hypothesis continues to spark intriguing debates about the nature of reality and consciousness. The simulation hypothesis proposes that our reality might be a computer simulation created by an advanced civilization. While this idea may sound like science fiction, it has garnered serious consideration from philosophers and scientists alike. Several lines of reasoning lend support to the simulation hypothesis. The rapid advancement of computer technology and virtual reality suggests that creating highly detailed simulations may be possible for sufficiently advanced civilizations. Some argue that the seemingly arbitrary constants in physics could be parameters set by the simulation creators. Additionally, certain quantum phenomena, such as the observer effect, have been interpreted as potential evidence of a simulated reality. However, there are also strong arguments against the simulation hypothesis. The sheer complexity of our universe, down to the quantum level, would require computational power far beyond anything we can currently conceive. Critics argue that the hypothesis is unfalsifiable, making it difficult to test scientifically. Furthermore, the lack of any observable glitches or inconsistencies in our reality challenges the notion of a simulated universe. Ultimately, while the simulation hypothesis remains an intriguing philosophical concept, concrete scientific evidence either supporting or refuting it remains elusive. As our understanding of the universe and computational capabilities continue to evolve, new insights may shed light on this fascinating question about the nature of our reality. The laws of physics in a simulated universe could potentially differ significantly from those in a real universe, depending on the design and capabilities of the simulation. In a simulated universe, the fundamental constants and rules governing reality would be defined by the programmers or creators of the simulation, rather than emerging naturally from the fabric of space-time. One key difference might be in the level of detail and complexity. A simulated universe might have simplified physics to reduce computational requirements, resulting in less nuanced interactions between particles or forces. For instance, quantum mechanics might be approximated or even omitted entirely, leading to a more deterministic and predictable universe than our own. The simulated universe could also have arbitrary limitations or boundaries that don't exist in a real universe. There might be a maximum speed for information or matter that's lower than the speed of light in our universe, or there could be a finite size to the simulated space. These constraints could lead to observable phenomena that would be impossible in our universe, such as objects disappearing when they reach the edge of the simulation. Furthermore, the laws of physics in a simulated universe might be mutable or inconsistent across time and space, unlike the uniform laws we observe in our universe. This could result in regions where gravity behaves differently or where the strong nuclear force has a different strength, leading to exotic phenomena that would challenge our understanding of reality. If our universe is indeed a simulation, the question of who or what might be running it opens up a fascinating realm of possibilities. Advanced civilizations far beyond our current level of technological development could be the architects of such a vast computational construct. These beings might possess intelligence and capabilities that are difficult for us to comprehend, operating on scales of time and space that dwarf our own existence. Alternatively, the simulation could be run by artificial intelligences that have far surpassed their original creators. These superintelligent entities might be exploring various scenarios of universal evolution, perhaps as a form of scientific inquiry or even entertainment. They could be studying the emergence of life and consciousness across different initial conditions and physical laws. Another intriguing possibility is that the simulation is a nested reality, where simulated beings within one level of reality have created simulations of their own, leading to a complex hierarchy of virtual universes. In this scenario, the ultimate base reality might be unknowable to us, as we could be many levels deep in this cascade of simulations. It is also conceivable that the nature of the simulation runners is so alien to our understanding that we lack the cognitive framework to even conceptualize their existence. They might exist in higher dimensions or operate according to principles that are fundamentally beyond our current scientific grasp, making any attempt to describe or understand them an exercise in futility. The simulation hypothesis poses a profound challenge to our understanding of reality. This idea suggests that our entire universe, including all of us within it, might be an incredibly advanced computer simulation created by a more technologically sophisticated civilization. At its core, this concept forces us to question the very nature of our existence and the world around us. Consider the rapid advancements in computer technology and virtual reality we've witnessed in recent decades. If we extrapolate this progress far into the future, it becomes conceivable that a civilization could create simulations so complex and detailed that they are indistinguishable from what we perceive as reality. The simulation hypothesis proposes that this may have already happened, and we are living inside one such simulation. This idea has far-reaching implications for our concept of reality. If true, it would mean that the physical laws we observe and the cosmos we study might be nothing more than programmed parameters in a vast computational system. Our thoughts, experiences, and even our consciousness could be the result of incredibly complex algorithms rather than emergent properties of biological brains. The simulation hypothesis also raises questions about the nature of free will and determinism. In a simulated reality, our actions and decisions might be predetermined by the program running the simulation, challenging our notion of autonomy and self-determination. This concept pushes us to reconsider fundamental philosophical questions about the nature of existence, consciousness, and the universe itself. The simulation hypothesis raises profound ethical questions that challenge our understanding of reality and our place in the universe. This concept suggests that our entire existence might be a computer simulation created by an advanced civilization, fundamentally altering our perception of free will and consciousness. If we are indeed living in a simulation, it forces us to reconsider the nature of our actions and their consequences. Are our choices truly our own, or are they predetermined by the parameters of the simulation? This dilemma extends to our understanding of morality and responsibility. If our reality is artificial, does that diminish the importance of ethical behavior? Furthermore, the simulation hypothesis introduces the unsettling possibility of a hierarchy of realities. If our world is simulated, there could be countless other simulations, each with its own conscious beings. This raises questions about the rights and moral status of simulated entities. Do the creators of a simulation have ethical obligations to their simulated beings? The implications extend to our scientific pursuits as well. If we are in a simulation, our understanding of physics and the universe might be limited by the constraints of the program. This could impact how we approach scientific research and technological advancement, potentially altering the course of human progress and our quest for knowledge about the true nature of reality. The simulation hypothesis proposes that our reality might be a computer-generated simulation created by an advanced civilization. This concept intertwines with ideas of determinism and free will in fascinating ways. In a simulated universe, every action and event could potentially be predetermined by the program running the simulation. This aligns closely with the philosophical concept of determinism, which suggests that all events are the inevitable result of prior causes. If our reality is indeed a simulation, it could mean that our thoughts, decisions, and actions are simply the output of complex algorithms, leaving little room for true free will. However, the nature of the simulation itself could impact the existence of free will. A sufficiently advanced simulation might incorporate genuine randomness or even allow for emergent properties that are not fully determined by its initial programming. In such a scenario, a form of free will might still be possible within the confines of the simulation. Furthermore, even if our reality is simulated, the question of free will becomes more complex when we consider the possibility of nested simulations. If we are in a simulation created by beings who themselves have free will, or if our simulated consciousness has somehow transcended its programming, the concept of free will might still apply. The simulation hypothesis thus adds new layers to the age-old debate between determinism and free will, challenging us to reconsider these concepts in light of potential technological realities. The question of whether we live in a simulation is a fascinating one that has intrigued scientists and philosophers alike. While it might seem like a concept straight out of science fiction, some researchers take this idea seriously and have proposed ways to potentially test it. One approach involves looking for telltale signs of a simulated reality. For instance, if our universe were a simulation, it might have built-in limitations to conserve computing power. These could manifest as a fundamental unit of time or space, or as patterns in the cosmic microwave background radiation that resemble those found in computer simulations. Another method suggests examining the behavior of cosmic rays. In a simulated universe, these high-energy particles might occasionally reveal glitches or errors in the system, similar to how video game characters sometimes clip through walls or floors due to programming limitations. However, proving or disproving the simulation hypothesis conclusively presents significant challenges. Any evidence we find could potentially be explained by alternative theories or simply be part of the simulation itself. Moreover, if we are indeed in a highly advanced simulation, its creators might have anticipated our attempts to detect it and designed it to be undetectable. Ultimately, while we can continue to explore this question through scientific inquiry and philosophical reasoning, a definitive answer may remain elusive. Mathematics serves as a powerful language for describing the universe, offering precision and clarity that ordinary language often lacks. This effectiveness stems from its ability to capture patterns and relationships in nature with remarkable accuracy. The universe appears to operate on fundamental principles that can be expressed through mathematical equations, allowing scientists to model complex phenomena and make predictions about the cosmos. The predictive power of mathematics in physics is particularly striking. Equations derived purely from mathematical reasoning have often led to the discovery of new particles or phenomena years or even decades later. This suggests a deep connection between mathematical structures and the fabric of reality itself. Some argue that mathematics is simply a human construct that happens to be useful for describing the world around us. However, the consistent success of mathematical models in explaining and predicting natural phenomena suggests a more profound link. It's as if the universe itself is written in the language of mathematics, with fundamental constants and equations governing everything from the behavior of subatomic particles to the expansion of the cosmos. This mathematical nature of the universe remains one of the most fascinating and mysterious aspects of our reality. It continues to drive scientific inquiry and philosophical debate, pushing us to explore the limits of our understanding and uncover the fundamental laws that govern our existence. The question of whether mathematics is discovered or invented has puzzled philosophers, mathematicians, and scientists for centuries. This fundamental debate touches on the very nature of mathematical truth and its relationship to the physical world. Those who argue that mathematics is discovered believe that mathematical truths exist independently of human minds, waiting to be uncovered. They point to the apparent universality of mathematical principles and how mathematical concepts seem to describe the natural world with uncanny accuracy. For example, the mathematical constant pi appears in numerous natural phenomena, from the spirals of galaxies to the shape of river meanders. On the other hand, proponents of the idea that mathematics is invented argue that mathematical concepts are human constructs, created to model and understand the world around us. They emphasize how mathematical systems, like imaginary numbers or non-Euclidean geometry, can be developed without direct correspondence to physical reality. These mathematical tools, while useful, may not necessarily reflect an underlying truth about the universe. The debate continues, with many mathematicians and scientists holding nuanced views that incorporate elements of both perspectives. Some argue that while basic mathematical concepts might be discovered, the complex systems built upon them are human inventions. Ultimately, this question intersects with deep philosophical issues about the nature of reality and human knowledge, making it a fascinating topic of ongoing discussion in the scientific community. Mathematical Platonism suggests that mathematical objects and structures exist independently of human thought, much like the fundamental laws of the universe. This philosophical stance posits that mathematics is not merely a human invention, but a discovery of eternal truths that exist beyond our physical reality. When we consider universal laws, such as gravity or the conservation of energy, we find striking parallels with mathematical Platonism. These laws appear to be constant throughout the observable universe, governing the behavior of celestial bodies and subatomic particles alike. Their consistency and universality hint at an underlying order that exists regardless of our ability to perceive or understand it. The connection between mathematical Platonism and universal laws becomes even more intriguing when we examine how mathematics consistently describes and predicts natural phenomena. From the elliptical orbits of planets to the wave functions of quantum mechanics, mathematical equations seem to capture the essence of reality with remarkable precision. This uncanny effectiveness of mathematics in describing the physical world has led some scientists and philosophers to wonder if the universe itself is fundamentally mathematical in nature. This relationship between abstract mathematical concepts and concrete physical laws raises profound questions about the nature of reality. Are the laws of physics simply mathematical truths manifested in the physical world, or does the success of mathematics in describing the universe stem from the evolution of our cognitive abilities within this reality? The interplay between mathematical Platonism and universal laws continues to fuel debates on the fundamental nature of existence and our place within it. Mathematical equations serve as a powerful language to describe and predict physical reality. They capture the fundamental laws and principles that govern the universe, allowing scientists to model complex phenomena with remarkable accuracy. These equations often reveal deep connections between seemingly unrelated aspects of nature, providing insights that might not be apparent through observation alone. In many cases, mathematical formulations have predicted the existence of particles or phenomena before they were experimentally observed. For instance, the equations of general relativity predicted the existence of black holes and gravitational waves decades before their actual detection. This predictive power demonstrates the profound link between abstract mathematical concepts and the tangible world around us. However, it is important to note that mathematical equations are models of reality, not reality itself. They are human constructs designed to approximate and understand the physical world. While incredibly useful and often astonishingly accurate, these models have limitations and can break down in extreme conditions or at the boundaries of our current understanding. The relationship between mathematics and physical reality remains a subject of philosophical debate. Some argue that mathematics is discovered rather than invented, suggesting that mathematical truths exist independently of human minds. Others view mathematics as a human creation, a tool we have developed to make sense of the world. Regardless of this debate, the undeniable effectiveness of mathematics in describing and predicting physical phenomena continues to drive scientific progress and deepen our understanding of the universe. The human mind has long grappled with the question of whether mathematics can fully describe our universe. While mathematics has proven incredibly effective in explaining many aspects of reality, from the motions of planets to the behavior of subatomic particles, some scientists and philosophers argue that there might be fundamental limits to its descriptive power. One perspective suggests that consciousness and subjective experiences might fall outside the realm of mathematical description. The qualitative nature of sensations like the redness of red or the taste of chocolate could potentially resist quantification. This idea, known as the hard problem of consciousness, remains a topic of intense debate in both scientific and philosophical circles. Another possibility is that certain aspects of quantum mechanics might defy complete mathematical description. The Copenhagen interpretation of quantum mechanics, for instance, posits that some quantum phenomena are inherently probabilistic and cannot be deterministically described. While mathematical models can predict probabilities, they might not capture the full essence of quantum reality. Furthermore, if our universe is infinitely complex, there could theoretically be aspects that lie beyond our capacity to describe mathematically, simply because our mathematical tools, no matter how advanced, might always fall short of capturing infinite complexity. However, this remains speculative, and many scientists maintain that mathematics, given its track record of success, will continue to be our most powerful tool for understanding the cosmos. Mathematics has been a driving force behind our deepening understanding of universal laws. As new mathematical concepts have emerged, they've provided scientists with powerful tools to describe and predict natural phenomena with increasing accuracy. One significant example is the development of calculus by Isaac Newton and Gottfried Leibniz. This mathematical framework allowed physicists to describe motion and change in precise terms, leading to a more comprehensive understanding of gravity and the movements of celestial bodies. Calculus became the foundation for classical mechanics and continues to be essential in modern physics. In the 20th century, the advent of non-Euclidean geometry paved the way for Albert Einstein's theory of general relativity. This revolutionary theory reframed our understanding of gravity as the curvature of spacetime, a concept that would have been impossible to formulate without the mathematical groundwork laid by mathematicians like Bernhard Riemann. More recently, the development of quantum mechanics has relied heavily on complex mathematical concepts such as Hilbert spaces and operator theory. These abstract mathematical ideas have enabled physicists to describe the bizarre behavior of subatomic particles, leading to technological advancements like transistors and lasers. As mathematics continues to evolve, it undoubtedly will unlock new insights into the fundamental laws that govern our universe. Symmetry serves as a fundamental principle in our understanding of the universe's laws. In physics, symmetries reveal deep connections between seemingly disparate phenomena and provide a powerful framework for describing nature's behavior. These symmetries manifest in various forms, from the simple rotational symmetry of a sphere to the more abstract symmetries of quantum fields. One of the most important aspects of symmetry in physics is its relationship to conservation laws. As discovered by mathematician Emmy Noether, every continuous symmetry in nature corresponds to a conserved quantity. For instance, the symmetry of time translation leads to the conservation of energy, while spatial translation symmetry results in the conservation of momentum. These conservation laws form the bedrock of our physical theories and help explain a wide range of observations. Symmetry also plays a crucial role in particle physics. The Standard Model, our most comprehensive theory of fundamental particles and forces, is built upon the principle of gauge symmetry. This mathematical concept allows us to describe the interactions between particles and fields in a consistent and unified manner. The discovery of the Higgs boson, for example, was a triumph of symmetry-based predictions in particle physics. Beyond particle physics, symmetry principles guide our understanding of the universe on the largest scales. The cosmological principle, which assumes the universe is homogeneous and isotropic on large scales, is essentially a statement of symmetry. This principle underpins modern cosmology and has led to groundbreaking theories about the origin and evolution of the universe, including the Big Bang model and the concept of cosmic inflation. Dimensionless constants in physics are fundamental numbers that do not have any units attached to them. These constants bridge the gap between the abstract world of mathematics and the physical reality we observe in the universe. They are pure numbers that emerge from the equations describing natural phenomena, often representing ratios or proportions that remain constant regardless of the units or scale used to measure them. One of the most famous dimensionless constants is the fine structure constant, which characterizes the strength of the electromagnetic interaction between elementary charged particles. This constant, approximately equal to 1 divided by 137, appears in various physical theories and equations, linking seemingly unrelated phenomena. These constants often arise from the combination of other physical constants in such a way that their units cancel out. For example, the ratio of the gravitational force to the electromagnetic force between two protons is a dimensionless constant. Such ratios allow physicists to compare the relative strengths of different fundamental forces in nature. Mathematically, dimensionless constants are significant because they often appear in equations describing universal behaviors or symmetries in nature. They represent fundamental truths about the universe that transcend specific measurement systems or scales. This universality makes them powerful tools for understanding the deep connections between different areas of physics and the underlying mathematical structures that govern our universe. Infinity plays a crucial role in both mathematics and physics, serving as a concept that pushes the boundaries of our understanding and calculations. In mathematics, infinity is not a number, but a concept representing something without limit or end. It allows mathematicians to work with and describe processes that continue without bound, such as the never-ending sequence of natural numbers. In physics, infinity often appears in theoretical models and calculations, particularly in areas like cosmology and quantum mechanics. However, physicists generally view infinities in their equations as signs that a theory or model needs refinement. The concept helps scientists explore extreme conditions such as the singularity at the center of a black hole or the proposed infinite density at the moment of the Big Bang. Infinity also connects to practical applications in technology and engineering. For instance, the idea of approaching infinity is crucial in calculus, which forms the basis for many physics equations used in designing everything from bridges to spacecraft. Additionally, contemplating infinity has philosophical implications, challenging our perceptions of the universe and our place within it. While infinity remains a powerful and useful concept, it also presents paradoxes and challenges. Scientists and mathematicians continue to grapple with its implications, making it a driving force for new discoveries and deeper understanding of our universe. The quest for a theory of everything has long captivated physicists and cosmologists. This ultimate theory would unite all fundamental forces and particles in the universe under a single, elegant mathematical framework. Currently, we have two powerful but seemingly incompatible theories: general relativity, which describes gravity and the behavior of space and time on large scales, and quantum mechanics, which governs the subatomic world. Many scientists believe that a theory of everything is possible and have proposed various candidates, such as string theory and loop quantum gravity. These theories attempt to reconcile the apparent contradictions between general relativity and quantum mechanics, offering a unified description of all matter and energy in the universe. However, developing and proving such a theory presents enormous challenges. The extreme conditions needed to test some aspects of these theories, such as the incredibly high energies present in the early universe, are currently beyond our experimental capabilities. Additionally, some physicists argue that a true theory of everything might be fundamentally impossible due to limitations in our ability to observe and measure the universe at its most fundamental level. Despite these challenges, the search for a theory of everything continues to drive scientific inquiry and push the boundaries of our understanding. If discovered, such a theory could revolutionize our comprehension of the cosmos, potentially unveiling new dimensions, explaining the nature of dark matter and dark energy, and even shedding light on the origin and fate of the universe itself. Our quest to understand the universe has led to remarkable discoveries, yet we face significant challenges that may limit our comprehension. The sheer scale of the cosmos, spanning billions of light years, presents a formidable obstacle. Much of the universe lies beyond our observable horizon, forever out of reach due to the expansion of space faster than the speed of light. The nature of our human brains, evolved to navigate the macroscopic world, struggles with concepts at the quantum scale and cosmic level. Ideas like quantum entanglement and the curvature of space-time often defy our intuition. This cognitive limitation might prevent us from fully grasping certain aspects of reality. Furthermore, our observations are constrained by our position within the universe and the tools we can create. Dark matter and dark energy, which constitute most of the cosmos, remain elusive and poorly understood. Their true nature might require detection methods beyond our current technological capabilities, or even beyond what is physically possible for us to develop. Lastly, there is the question of whether mathematics, our primary language for describing the universe, is truly sufficient to capture all of reality. Some phenomena might exist that cannot be described by any mathematical framework we can conceive. These fundamental limits challenge our ability to gain a complete understanding of the cosmos, leaving us to wonder if there will always be mysteries beyond our grasp. Cognitive biases significantly influence how we interpret and understand the laws governing our universe. These mental shortcuts, which our brains have developed over time, can lead us to misinterpret or oversimplify complex cosmic phenomena. For instance, our tendency towards pattern recognition often causes us to see order where none exists, potentially leading to misunderstandings about the nature of cosmic structures or the distribution of galaxies. Our inherent bias towards anthropocentrism can also skew our perception of universal laws. We often unconsciously project human characteristics or Earth-based experiences onto cosmic phenomena, which can result in misconceptions about the true nature of the universe. This bias can make it challenging to grasp concepts that are far removed from our everyday experiences, such as the curvature of space-time or the quantum behavior of particles. Confirmation bias plays a role in how we interpret new astronomical discoveries or theories. We tend to seek out information that confirms our existing beliefs about the universe, potentially overlooking evidence that contradicts our preconceptions. This can slow down scientific progress and hinder our ability to update our understanding of cosmic laws as new data becomes available. The anchoring effect, where we rely too heavily on the first piece of information we receive, can also impact our interpretation of universal laws. Initial theories or explanations about cosmic phenomena can become deeply ingrained, making it difficult to accept new, more accurate models, even when presented with compelling evidence. This cognitive bias underscores the importance of remaining open to new ideas and continuously questioning our understanding of the cosmos. Language serves as a powerful tool in our quest to describe and understand the laws that govern our universe. It allows us to articulate complex concepts, share ideas, and build upon the knowledge of generations before us. Through carefully chosen words and precise terminology, scientists can communicate their observations and theories about the cosmos to both their peers and the general public. The development of specialized scientific language has been crucial in advancing our understanding of universal laws. Terms like gravity, relativity, and quantum mechanics encapsulate entire fields of study, enabling researchers to discuss intricate phenomena with clarity and precision. This shared vocabulary facilitates collaboration across borders and cultures, accelerating scientific progress on a global scale. However, language can also present limitations in our ability to fully grasp and express certain universal concepts. Some aspects of quantum mechanics or higher dimensional mathematics, for instance, challenge our everyday linguistic frameworks. In these cases, scientists often turn to mathematical equations and models to describe phenomena that defy conventional language. Despite these challenges, language remains our primary means of disseminating scientific knowledge to the wider world. It bridges the gap between abstract theories and public understanding, allowing us to contemplate the wonders of the universe and inspiring future generations to explore the cosmos further. As our understanding of universal laws grows, so too does our ability to describe them, constantly pushing the boundaries of human expression and comprehension. Our perception of time fundamentally shapes how we interpret causality and natural laws. We experience time as a linear progression, with events occurring in a specific order. This linear perspective leads us to view cause and effect as a straightforward sequence, where one event directly leads to another. The human brain is wired to seek patterns and connections, often interpreting coincidences as causal relationships. This tendency, while useful for survival, can sometimes lead to misunderstandings about the true nature of physical laws. For instance, we might assume that because one event consistently precedes another, it must be the cause, when in reality, the relationship could be more complex or even unrelated. Our time-bound perception also influences how we understand natural laws. We observe phenomena unfolding over time, which allows us to formulate theories and predictions. However, this perspective can limit our ability to grasp concepts that operate outside our familiar time framework, such as quantum entanglement or the behavior of subatomic particles. At larger scales, our perception of time affects how we interpret cosmic events. The vast distances in space mean that we observe celestial phenomena as they appeared in the past, not as they exist now. This delay between occurrence and observation adds another layer of complexity to our understanding of causality and natural laws in the universe, challenging us to think beyond our immediate temporal experience. The quest for knowledge has driven humanity's progress, yet there are indeed aspects of reality that may be inherently unknowable. This concept challenges our understanding of the universe and the limits of human comprehension. One area where we encounter unknowable aspects is in quantum mechanics. The Heisenberg uncertainty principle states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. This limitation is not due to the imperfection of our measuring tools, but rather a fundamental property of the universe itself. Another potentially unknowable realm lies beyond the observable universe. Due to the expansion of space and the finite speed of light, there are regions of the cosmos from which light has not had time to reach us since the Big Bang. These areas remain forever outside our ability to observe or study directly. Consciousness presents yet another frontier of the unknowable. While we can study brain activity and behavior, the subjective experience of consciousness, how it feels to be aware, remains elusive to scientific inquiry. Some philosophers argue that this hard problem of consciousness may be inherently unsolvable through objective means. Our understanding of universal laws has been profoundly influenced by the cultural and historical contexts in which scientific discoveries have taken place. Throughout history, different civilizations have developed their own explanations for natural phenomena, often intertwining these ideas with religious or philosophical beliefs. These early attempts to make sense of the cosmos laid the groundwork for modern scientific inquiry. Ancient Greek philosophers, for instance, proposed atomic theories and geometric models of the universe that continue to shape our thinking today. The Islamic Golden Age saw advancements in mathematics and astronomy that were crucial for later European scientific developments. During the Renaissance and Enlightenment periods, a shift towards empirical observation and experimentation began to challenge long-held beliefs about the nature of reality. The scientific revolution of the 16th and 17th centuries marked a turning point in our approach to understanding universal laws. This era saw the emergence of key figures like Galileo, Newton, and Kepler, whose work established the foundations of classical physics. Their discoveries were not made in isolation, but were deeply influenced by the intellectual and social climate of their time, including religious doctrines and political structures. In the modern era, our understanding of universal laws continues to be shaped by cultural factors. The global nature of scientific research today means that diverse perspectives contribute to our collective knowledge. Technological advancements, societal values, and even geopolitical events all play a role in determining which areas of research receive funding and attention, ultimately influencing the direction of scientific progress and our evolving comprehension of the universe's fundamental principles. Intuition plays a crucial part in scientific discovery and understanding, often serving as the spark that ignites groundbreaking research. Scientists frequently describe moments of insight or hunches that lead them to explore new avenues of inquiry. These flashes of intuition can help researchers connect seemingly unrelated concepts or envision novel solutions to complex problems. However, intuition alone is not enough in the scientific process. It must be paired with rigorous experimentation, data collection, and analysis to verify or disprove the initial hunch. Many great scientific discoveries began with an intuitive leap, but were only accepted after extensive testing and peer review. Intuition also aids scientists in interpreting complex data sets or experimental results. Experienced researchers often develop a feel for their field, allowing them to quickly identify patterns or anomalies that might escape a less seasoned observer. This intuitive understanding can guide further investigation and lead to new discoveries. While intuition is valuable, scientists must remain vigilant against allowing it to bias their work. The scientific method serves as a safeguard, ensuring that intuitive ideas are thoroughly tested and validated before being accepted as scientific fact. Balancing intuition with methodical investigation is key to advancing our understanding of the universe. The scientific method serves as a powerful tool in our quest to unravel the mysteries of the universe. By providing a structured approach to inquiry, it allows us to systematically explore and test ideas about how the cosmos operates. This method begins with observation, leading to questions and hypotheses that can be rigorously tested through experiments and data collection. One of the key strengths of the scientific method is its ability to help us overcome our inherent biases and preconceptions. It demands that we base our conclusions on evidence rather than intuition or wishful thinking. This objectivity is crucial when dealing with concepts that often defy our everyday experiences, such as quantum mechanics or the nature of dark matter. Moreover, the scientific method encourages repeatability and peer review. This means that findings can be verified independently by other researchers, ensuring that our understanding of universal laws is built on a solid foundation. When multiple scientists across the world can reproduce the same results, it strengthens our confidence in the conclusions drawn. The iterative nature of the scientific method also allows for continuous refinement of our knowledge. As new technologies and techniques emerge, we can revisit and test previous theories with greater precision. This ongoing process of questioning and testing helps us gradually push back the boundaries of our understanding, revealing ever more profound insights into the fundamental laws that govern our universe. Gödel's incompleteness theorems have profound implications for our understanding of reality, challenging our notions of mathematical certainty and the limits of human knowledge. These theorems, developed by mathematician Kurt Gödel in the 1930s, reveal fundamental limitations in formal logical systems. The first incompleteness theorem shows that for any consistent formal system complex enough to represent basic arithmetic, there will always be statements that are true within the system but cannot be proven using the system's own rules. This means that no matter how comprehensive our mathematical or logical framework becomes, there will always be truths that lie beyond its reach. This insight extends beyond pure mathematics, suggesting that our attempts to fully describe and understand reality through formal systems may be inherently limited. It raises the possibility that there might be aspects of the universe that are true but unprovable within our current scientific and philosophical frameworks. The second incompleteness theorem further complicates matters by demonstrating that a consistent system cannot prove its own consistency. This calls into question our ability to establish the reliability of our foundational theories about reality. Together, these theorems hint at a deeper, perhaps unknowable structure to the universe, reminding us of the boundaries of human comprehension and the ever-present potential for discovery beyond our current understanding. As artificial intelligence continues to advance at a rapid pace, the question of whether it could surpass human ability to understand universal laws becomes increasingly relevant. AI systems have already demonstrated remarkable capabilities in processing vast amounts of data and recognizing complex patterns, often exceeding human performance in specific tasks. In the realm of scientific discovery, AI has shown promise in areas such as particle physics and astronomy. These systems can analyze enormous datasets, identify subtle correlations, and even propose new hypotheses that human scientists might overlook. This ability to process and interpret information at an unprecedented scale could potentially lead to breakthroughs in our understanding of fundamental physical laws. However, it is important to note that human intuition, creativity, and abstract thinking have been crucial in developing our current understanding of the universe. The ability to form conceptual frameworks, ask profound questions, and make intuitive leaps has been a hallmark of human scientific progress. While AI can excel at pattern recognition and data analysis, it may still struggle with these more abstract aspects of scientific inquiry. Ultimately, the future of scientific discovery might lie in a symbiotic relationship between human scientists and AI systems. By combining the strengths of both artificial and human intelligence, we may unlock new insights into the fundamental laws governing our universe, potentially surpassing what either could achieve alone. Emergence in the context of universal laws refers to the fascinating phenomenon where complex systems and behaviors arise from simpler underlying rules or interactions. In our universe, we observe intricate patterns and structures that seem to transcend the basic physical laws governing individual particles or components. At the most fundamental level, our universe operates on a set of simple physical laws. These laws dictate how particles interact, how forces behave, and how energy and matter relate to each other. However, as we zoom out from this microscopic scale, we begin to see behaviors and properties that cannot be easily predicted or explained by these fundamental laws alone. For instance, the laws of quantum mechanics govern the behavior of subatomic particles, yet they give rise to the diverse properties of atoms and molecules. These atoms and molecules, in turn, combine to form complex structures like crystals, proteins, and even living organisms. Each level of organization exhibits new properties and behaviors that emerge from the interactions of its constituent parts. This concept of emergence extends beyond the realm of physics and chemistry. In biology, the simple rules of natural selection lead to the incredible diversity and complexity of life on Earth. In cosmology, the basic forces of gravity and electromagnetism result in the formation of stars, galaxies, and the large-scale structure of the universe. Emergence reminds us that the whole is often greater than the sum of its parts, and that our universe is a tapestry of interconnected systems, each level building upon the last to create the rich and complex cosmos we observe. Complex systems emerge from simple rules through a fascinating process of self-organization and emergence. In nature and the universe, we often see intricate patterns and behaviors that seem far too sophisticated to arise from basic principles. Yet, time and again, we discover that complexity can indeed spring from simplicity. Take, for example, the formation of snowflakes. Each unique and intricate snowflake begins with a simple set of rules governing how water molecules bond in cold conditions. As more molecules join, they follow these same rules, but their interactions lead to increasingly complex structures. The end result is a stunning display of symmetry and detail, all arising from fundamental physical laws. Similarly, in the realm of biology, the diverse and complex ecosystems we see today evolved from basic principles of natural selection and genetic variation. Over millions of years, these simple rules have given rise to an astounding array of life forms, each adapted to its environment in remarkable ways. Even in the cosmos, we see complexity emerging from simplicity. The vast web-like structure of the universe, with its clusters of galaxies and enormous voids, can be traced back to tiny quantum fluctuations in the early universe, amplified over time by gravity. From these humble beginnings, following the basic laws of physics, the rich tapestry of the cosmos unfolds before us, revealing that even the grandest structures can arise from the simplest of origins. The question of whether emergent phenomena can be reduced to fundamental laws is a complex and ongoing debate in science and philosophy. Emergent phenomena are those that arise from the interactions of simpler components but exhibit properties or behaviors that cannot be easily predicted or explained by studying those components in isolation. On one hand, many scientists argue that all phenomena, including emergent ones, should ultimately be explainable through fundamental physical laws. They contend that with sufficient knowledge and computational power, we could theoretically trace any emergent behavior back to its constituent parts and their interactions. However, others argue that emergent phenomena possess a level of complexity that makes them irreducible to simpler components. They suggest that new properties and laws emerge at higher levels of organization that cannot be fully captured by studying the underlying parts alone. This view posits that there may be fundamental principles governing emergent behavior that are distinct from the laws governing individual components. The debate surrounding emergent phenomena and reductionism continues to shape our understanding of complex systems across various scientific disciplines, from physics and chemistry to biology and neuroscience. As we delve deeper into the nature of emergence, we may gain new insights into the fundamental structure of reality and the limits of our ability to explain the universe through reductionist approaches. Reductionism and emergence represent two fundamental approaches to understanding complex systems in science. Reductionism seeks to explain phenomena by breaking them down into their smallest components, while emergence focuses on how new properties and behaviors arise from the interactions of simpler parts. Reductionism has been a powerful tool in scientific discovery, allowing researchers to uncover the basic building blocks of matter and life. It has led to breakthroughs in fields such as particle physics and molecular biology. However, this approach has limitations when dealing with highly complex systems. Emergence, on the other hand, acknowledges that some phenomena cannot be fully explained by studying their individual components alone. It recognizes that the whole can be greater than the sum of its parts. Examples of emergent properties include consciousness arising from neural networks, or the behavior of ant colonies emerging from the actions of individual ants. The relationship between reductionism and emergence is not one of opposition, but rather complementarity. Both approaches are valuable in scientific inquiry, with reductionism providing a foundation for understanding basic elements and emergence offering insights into how these elements interact to create higher-level phenomena. This dual perspective enables scientists to gain a more comprehensive understanding of the natural world, from the smallest subatomic particles to the vast complexities of ecosystems and the universe itself. Emergence challenges our traditional understanding of causality by revealing complex behaviors and properties that arise from simple interactions, defying straightforward cause and effect relationships. In emergent systems, the whole becomes greater than the sum of its parts, producing outcomes that cannot be easily predicted or explained by examining individual components alone. Consider a flock of birds in flight. The intricate patterns they form emerge from basic rules followed by each bird, such as maintaining a certain distance from neighbors and matching their speed. Yet the resulting swarm behavior is not directed by any single bird or external force. This exemplifies how local interactions can lead to global phenomena that seem to have a life of their own. In the realm of physics, emergence manifests in phenomena like superconductivity and phase transitions. These properties appear suddenly when a system reaches a critical point, despite being absent in the constituent particles. Such emergent behaviors force us to reconsider linear causality and embrace a more holistic view of nature. Emergence also plays a crucial role in fields like neuroscience and artificial intelligence. The human mind, with its capacity for consciousness and complex thought, emerges from the interactions of billions of neurons. Similarly, sophisticated artificial intelligence can arise from networks of simple processing units. These examples highlight how emergence blurs the lines between cause and effect, challenging us to develop new frameworks for understanding the world around us. Self-organization plays a crucial role in the emergence of complex systems throughout the universe. This fundamental process allows intricate structures and behaviors to arise spontaneously from simpler components without external guidance or control. In cosmic systems, self-organization manifests in the formation of galaxies and star clusters. Vast clouds of gas and dust, influenced by gravity and other forces, gradually coalesce into organized structures. Over time, these structures develop distinct shapes and patterns, from spiral galaxies to globular clusters, all through the interplay of basic physical laws. On smaller scales, self-organization is evident in planetary formation. As particles in protoplanetary disks collide and combine, they form larger bodies that exert greater gravitational influence. This process continues, leading to the emergence of planets, moons, and asteroid belts, each with its own unique characteristics. Even in biological systems, self-organization is a driving force. From the formation of complex molecules to the development of living organisms, simple components interact to create increasingly sophisticated structures and functions. This process underlies the very fabric of life itself, demonstrating how complexity can arise from simplicity through natural, unguided processes. The concept of emergence and the laws of thermodynamics are intricately connected, revealing fascinating insights into the nature of our universe. Emergence refers to the way complex systems and patterns arise from relatively simple interactions. This phenomenon is deeply rooted in the fundamental principles described by thermodynamics. The second law of thermodynamics, which deals with entropy and the tendency of systems to move towards disorder, plays a crucial role in emergence. As energy disperses and entropy increases, it creates conditions that allow for the spontaneous formation of organized structures. This might seem counterintuitive, but it's the very drive towards disorder that enables order to emerge in localized areas. Consider how planets and stars form from scattered cosmic dust. The overall entropy of the universe increases as gravity pulls matter together, releasing heat. Yet within this process, highly organized structures emerge. Similarly, life itself is an emergent phenomenon, creating local pockets of order while increasing entropy in the surrounding environment. The interplay between energy, entropy, and information is key to understanding emergence in the context of thermodynamics. As systems exchange energy and matter with their surroundings, they can self-organize into more complex states. This self-organization is not a violation of thermodynamic laws, but rather a consequence of them, demonstrating how the fundamental rules of the universe give rise to the intricate structures and phenomena we observe around us. The concept of emergence offers a fascinating perspective on the origin of life in the universe. Emergence describes how complex systems and patterns arise from relatively simple interactions. In the context of life's origins, it suggests that the building blocks of life, simple organic molecules, could have combined in increasingly complex ways, eventually giving rise to self-replicating systems and, ultimately, living organisms. This idea aligns with current scientific understanding of how life might have begun on Earth. In primordial oceans, basic chemical compounds likely formed more complex molecules through repeated interactions. Over time, these molecules may have developed the ability to catalyze their own reproduction, a crucial step towards what we define as life. Emergence also helps explain how simple cells could have evolved into the diverse and complex life forms we see today. Each level of biological organization, from molecules to cells to organisms, exhibits emergent properties not present in its individual components. This bottom-up approach to complexity provides a compelling framework for understanding life's origins without invoking external design. However, while emergence offers valuable insights, it does not yet provide a complete explanation for life's origins. Scientists continue to investigate the specific conditions and processes that could have led to the emergence of life, both on Earth and potentially elsewhere in the universe. The study of emergence in relation to life's origins remains an active and exciting area of research in astrobiology and origin of life studies. Emergence plays a crucial role in shaping our understanding of consciousness, offering a fascinating perspective on how complex mental phenomena arise from simpler neurological processes. This concept suggests that consciousness is not a singular, easily definable entity, but rather a sophisticated interplay of various brain functions working in concert. At its core, emergence describes how intricate systems and behaviors can develop from relatively simple rules or components. In the context of consciousness, this means that our subjective experiences, thoughts, and self-awareness might emerge from the collective activity of billions of neurons in our brains. These individual neurons, following basic electrochemical principles, somehow give rise to the rich tapestry of human consciousness. This emergent view challenges traditional notions of consciousness as a unitary phenomenon, instead framing it as a dynamic process that arises from the integration of multiple cognitive functions. It helps explain why consciousness is so difficult to pin down or replicate artificially, as it is not localized to a single area of the brain, but emerges from the complex interactions across various neural networks. The concept of emergence in consciousness also aligns with observed phenomena in neuroscience, such as how small changes in neural activity can lead to significant shifts in conscious experience. This perspective encourages researchers to look beyond individual brain regions and consider the holistic patterns of neural activity that might give rise to our sense of self and awareness of the world around us. The idea that universal laws might be emergent phenomena is a fascinating concept that challenges our understanding of the cosmos. As we delve deeper into the nature of reality, scientists and philosophers have begun to question whether the fundamental laws we observe are truly fundamental or if they arise from simpler, more basic principles. This notion suggests that the laws governing our universe, such as gravity, electromagnetism, and the strong and weak nuclear forces, might not be fixed and eternal. Instead, they could be the result of more primitive rules or conditions that existed in the early universe. As the cosmos evolved and expanded, these underlying principles could have given rise to the complex set of laws we observe today. One intriguing aspect of this concept is the possibility that different regions of the universe, or even other universes, might have different emergent laws. This could explain why our universe appears to be fine-tuned for life, as it might be one of many cosmic regions with varying sets of emergent laws. Some theoretical physicists propose that the fundamental constants and laws we observe could be analogous to the properties of materials, which emerge from the collective behavior of countless atoms and molecules. While this idea remains speculative, it opens up new avenues for understanding the nature of reality and the origins of the universe. If universal laws are indeed emergent, it could revolutionize our approach to physics and cosmology, potentially leading to a more unified theory of everything that explains not just how the universe works, but why it works the way it does. At the heart of our universe lies a profound connection between information and physical laws. This relationship forms the foundation of our understanding of reality, shaping how we perceive and interact with the world around us. Physical laws, such as gravity, electromagnetism, and thermodynamics, govern the behavior of matter and energy throughout the cosmos. These laws are essentially descriptions of how information is processed and transferred within the universe. For instance, when two objects attract each other due to gravity, they are exchanging information about their mass and position. Moreover, the concept of entropy, central to thermodynamics, is intimately tied to information. As systems become more disordered, they lose the ability to convey specific information. This loss of information is a fundamental aspect of the arrow of time, explaining why we perceive time as moving forward. Quantum mechanics further blurs the line between information and physical reality. The act of measurement, which involves gathering information about a quantum system, can actually influence the state of that system. This suggests that information is not just a passive description of reality, but an active participant in shaping it. Entropy and information are deeply intertwined concepts that bridge the realms of physics and communication. In thermodynamics, entropy measures the degree of disorder in a system, while in information theory, it quantifies the amount of uncertainty in a message. This connection reveals a fundamental link between the physical world and the abstract realm of data. When we consider information, entropy relates to the unpredictability of a message. A highly predictable message, such as a string of identical letters, has low entropy and conveys little new information. Conversely, a message with high entropy contains more surprises and thus more information. This parallels the thermodynamic notion of entropy, where a more disordered system has higher entropy and more potential states. The relationship between entropy and information becomes particularly evident in data compression. Efficient compression algorithms exploit patterns and redundancies in data, essentially reducing its entropy. By identifying and eliminating predictable elements, these algorithms can represent information more compactly, much like how a well-organized system has lower entropy than a chaotic one. Understanding this connection has profound implications for fields ranging from cryptography to quantum computing. In secure communications, high entropy is desirable as it makes messages harder to predict and decrypt. In quantum systems, the concept of entanglement entropy provides insights into the nature of quantum information and its behavior across space and time. The holographic principle represents a groundbreaking idea in theoretical physics that challenges our fundamental understanding of space, time, and the nature of reality itself. This principle suggests that all the information contained within a region of space can be described on its boundary. To grasp this concept, imagine a three-dimensional object, like a sphere. The holographic principle proposes that all the information about that sphere, including its volume and contents, can be encoded on its two-dimensional surface. This notion extends to our entire universe, implying that the three-dimensional world we experience might be a projection of information stored on a two-dimensional surface. The holographic principle emerged from studies of black holes and string theory. It offers potential solutions to long-standing puzzles in physics, such as reconciling quantum mechanics with gravity. By reducing the dimensions needed to describe our universe, it provides a new framework for understanding the nature of space and time. While still theoretical, the holographic principle has profound implications for our understanding of reality. It suggests that the universe might operate like a vast hologram, with our perceived three-dimensional world emerging from information encoded on a distant, two-dimensional surface. This principle continues to inspire new avenues of research and could potentially lead to a more unified theory of the cosmos. Quantum information theory fundamentally reshapes our perception of reality by revealing a world that defies classical intuition. At its core, this field explores how information behaves when governed by the strange rules of quantum mechanics. Unlike classical bits that exist in definite states of 0 or 1, quantum bits or qubits can exist in multiple states simultaneously, a phenomenon known as superposition. This superposition principle leads to counterintuitive effects. For instance, quantum entanglement allows particles to instantaneously influence each other regardless of the distance between them, seemingly violating the speed of light limit. This non-local behavior suggests a deeper connection between particles that transcends our everyday understanding of space and time. Quantum information theory also introduces the concept of quantum uncertainty, which asserts that certain pairs of physical properties cannot be simultaneously known with perfect accuracy. This inherent fuzziness in nature challenges our notion of a deterministic universe and raises profound questions about the nature of measurement and observation. Moreover, the field hints at the possibility that information might be a fundamental building block of reality, potentially more basic than matter or energy. This idea challenges our classical view of the universe and suggests that the fabric of reality might be woven from quantum information itself, forcing us to reconsider our most basic assumptions about the nature of existence. The concept of information as the fundamental building block of the universe is a fascinating idea that has gained traction among some physicists and philosophers. This perspective suggests that at its most basic level, reality might be composed not of particles or energy, but of bits of information. This idea stems from the field of quantum mechanics, where the behavior of particles can be described in terms of probability and information. In quantum systems, the act of measurement itself seems to play a crucial role in determining the state of a particle, leading some scientists to propose that information might be more fundamental than matter. The holographic principle, developed by theoretical physicists, further supports this notion. It proposes that all the information contained within a volume of space can be described on its boundary. This principle has led to speculation that our three-dimensional reality might be a projection of information stored on a two-dimensional surface. While intriguing, it is important to note that the idea of the universe being fundamentally composed of information remains speculative. It challenges our conventional understanding of reality and requires further research and evidence to be fully accepted by the scientific community. Nonetheless, it opens up exciting possibilities for our understanding of the cosmos and the nature of existence itself. The measurement problem in quantum mechanics revolves around the fundamental role of information and observation. At its core, this enigma challenges our understanding of how the act of measurement affects quantum systems. In quantum mechanics, particles exist in a superposition of states until they are observed or measured. This means that before measurement, a particle can potentially occupy multiple states simultaneously. However, when we attempt to gather information about the system through measurement, this superposition collapses into a single, definite state. The role of information in this context is twofold. First, it relates to what we can know about a quantum system before measurement. The Heisenberg uncertainty principle tells us that there are inherent limits to the precision with which we can simultaneously measure certain pairs of physical properties, such as position and momentum. This limitation on information is not due to technological constraints, but is a fundamental aspect of quantum reality. Secondly, information plays a crucial role in the act of measurement itself. The very process of obtaining information about a quantum system irrevocably changes that system. This leads to profound questions about the nature of reality and the role of the observer. Does consciousness play a part in collapsing the wave function? Or does the interaction between the quantum system and the measuring apparatus alone cause the collapse? These questions highlight the deep connection between information, measurement, and the fundamental nature of quantum reality. The concept of information is deeply intertwined with the arrow of time, providing a fascinating perspective on why time seems to flow in one direction. In our everyday experience, we observe events unfolding in a specific sequence, never witnessing them in reverse. This one-way progression of time is closely linked to the flow of information in the universe. At its core, this relationship stems from the second law of thermodynamics, which states that the entropy or disorder of an isolated system always increases over time. When we consider information in this context, we can think of it as a measure of the complexity and organization within a system. As entropy increases, the amount of useful information in a system tends to decrease. This loss of information manifests in numerous ways throughout the universe. For instance, when we mix hot and cold water, the temperature evens out, and we lose the initial information about which parts were hot and which were cold. Similarly, when we burn a piece of paper, the information contained in the writing is lost, scattered into the environment as heat and ash. These processes are irreversible without additional energy input, aligning with our perception of time's forward march. The link between information and the arrow of time becomes even more profound when we consider quantum mechanics. In quantum systems, the act of measurement itself can be seen as a process that creates information while simultaneously collapsing the wave function and reducing the system's quantum possibilities. This irreversible creation of information through observation further reinforces the unidirectional nature of time as we experience it. Quantum entanglement is a fascinating phenomenon in the realm of quantum physics. It occurs when two or more particles become connected in such a way that the quantum state of each particle cannot be described independently, even when separated by vast distances. This connection is so profound that measuring the state of one particle instantly affects the state of its entangled partner, regardless of how far apart they are. This strange behavior has significant implications for information theory and communication. In the world of quantum entanglement, information about the state of one particle can be instantaneously transmitted to its entangled partner. This seemingly defies the speed of light, which we typically consider the universal speed limit for information transfer. Scientists are exploring how to harness quantum entanglement for practical applications. One exciting area is quantum computing, where entangled particles could potentially process information much faster than traditional computers. Another is quantum cryptography, which could use entanglement to create unbreakable codes for secure communication. However, many mysteries remain about how quantum entanglement truly works and what its limits are. As researchers continue to unravel its secrets, quantum entanglement may revolutionize our understanding of information, communication, and the fundamental nature of reality itself. The concept of information conservation in the universe is a fascinating and complex topic that has gained significant attention in modern physics. Much like energy, which we know is conserved according to the laws of thermodynamics, some scientists propose that information might also be preserved throughout the cosmos. This idea stems from quantum mechanics and our understanding of black holes. When objects fall into a black hole, they seem to disappear completely, along with all the information they contain. However, this apparent loss of information conflicts with the principles of quantum mechanics, which suggest that information should never be truly lost. To resolve this paradox, physicists have proposed various theories. One prominent idea is the holographic principle, which suggests that all the information contained within a region of space can be described on its boundary. In the context of black holes, this would mean that information about everything that falls into a black hole might be encoded on its event horizon. Another intriguing possibility is that information might be preserved through quantum entanglement, a phenomenon where particles remain connected even when separated by vast distances. This could potentially allow information to escape from black holes through subtle quantum effects, ensuring its conservation across the universe. The processing of information is intimately connected to the laws of thermodynamics, particularly the second law. This fundamental principle of physics states that the total entropy of an isolated system always increases over time. In the context of information processing, entropy can be understood as a measure of disorder or uncertainty in a system. When we process information, whether in our brains or in computers, we are essentially organizing data and reducing uncertainty. This organization requires energy and inevitably produces heat as a byproduct. The energy used to process information cannot be perfectly efficient, and some of it is always lost as waste heat, increasing the overall entropy of the system. This relationship between information and thermodynamics was first explored by physicist Rolf Landauer in the 1960s. He proposed that erasing information, which is a crucial part of information processing, always results in an increase in entropy. This principle, known as Landauer's principle, sets a theoretical minimum amount of energy required to erase one bit of information. The implications of this connection are far-reaching. It suggests that there are fundamental physical limits to the efficiency of computation and information processing. As we strive to create more powerful and efficient computers, we are ultimately constrained by these thermodynamic principles, highlighting the deep interplay between information theory and the fundamental laws of physics. The anthropic principle is a fascinating concept in cosmology that attempts to explain why our universe appears to be perfectly suited for human life. It suggests that the fundamental constants and laws of physics we observe are not random, but rather finely tuned to allow for the existence of intelligent observers like ourselves. This principle comes in two main forms. The weak anthropic principle simply states that we should not be surprised to find ourselves in a universe capable of supporting life, as we could not exist to observe it otherwise. The strong anthropic principle goes further, proposing that the universe must have properties that allow life to develop within it. Critics argue that the anthropic principle is not truly explanatory, as it can be seen as a form of circular reasoning. However, proponents suggest it can help explain why our universe seems so improbably hospitable to life, given the vast number of possible configurations of physical laws and constants. The anthropic principle has implications for our understanding of the cosmos and our place within it. It raises questions about the potential existence of multiple universes and the nature of reality itself, challenging us to consider our cosmic significance in new and thought-provoking ways. The fine-tuning of universal constants plays a crucial role in the existence of life as we know it. These constants, such as the strength of gravity, the speed of light, and the charge of an electron, have precise values that allow for the formation of stable atoms, stars, and galaxies. If any of these constants were even slightly different, the universe might not support complex structures or life. For instance, if the strong nuclear force were marginally weaker, protons and neutrons would not bind together, preventing the formation of atomic nuclei. Conversely, if it were slightly stronger, all hydrogen would fuse into heavier elements, leaving no fuel for stars. The delicate balance of these forces allows for the creation of the diverse elements necessary for life. Similarly, the cosmological constant, which relates to the expansion rate of the universe, is fine-tuned to an astonishing degree. If it were slightly larger, the universe would expand too rapidly for galaxies and stars to form. If it were smaller, the universe would collapse before life could emerge. This precise calibration creates conditions conducive to the development of complex organisms. The apparent fine-tuning of these constants has led to much scientific debate. Some argue it suggests a purposeful design, while others propose the existence of multiple universes with varying constants, where we happen to exist in one capable of supporting life. Regardless of the interpretation, the delicate balance of these universal constants remains a fascinating aspect of our cosmos and its potential for harboring life. The anthropic principle comes in several forms, each offering a different perspective on the relationship between the universe and intelligent life. The weak anthropic principle suggests that the observable universe must have properties that allow for the existence of observers. This version simply states that we should not be surprised to find ourselves in a universe capable of supporting life, as we could not exist to observe it otherwise. The strong anthropic principle takes this idea further, proposing that the universe must have properties that allow life to develop at some point in its history. This version implies a more purposeful universe, one that is somehow compelled to bring about the conditions necessary for intelligent observers. Another variation is the participatory anthropic principle, which posits that observers are necessary to bring the universe into existence. This interpretation draws on concepts from quantum mechanics, suggesting that the act of observation plays a crucial role in determining the nature of reality. The final anthropic principle proposes that intelligent life must come into existence in the universe, and once it does, it will never die out. This version speculates on the long-term survival and evolution of intelligent life, suggesting that it might play a fundamental role in the cosmos. The anthropic principle presents a fascinating perspective on the nature of our universe and our place within it. This principle observes that the fundamental constants and laws of physics appear to be finely tuned to allow for the existence of life as we know it. Even small changes to these constants could result in a universe incapable of supporting complex structures, let alone conscious beings. This observation has led to intense debate about its implications for the existence of a universe creator. Some argue that the apparent fine-tuning suggests intentional design, pointing to a creator who set the universe's parameters specifically to allow for life. They contend that the precise balance required for our existence is too improbable to have occurred by chance. However, others interpret the anthropic principle differently. They propose that our universe might be one of many in a vast multiverse. In this scenario, each universe could have different fundamental constants, and we simply find ourselves in one capable of supporting life because that is the only type where observers can exist. This interpretation does not require a creator, instead relying on the sheer number of possible universes to explain our life-friendly conditions. Ultimately, the anthropic principle does not definitively prove or disprove the existence of a universe creator. Instead, it highlights the remarkable conditions necessary for our existence and prompts us to question why our universe appears so well suited for life. This principle continues to fuel scientific inquiry and philosophical debate, reminding us of the profound mysteries that still surround our understanding of the cosmos and our place within it. The anthropic principle, which suggests that the universe's fundamental constants are fine-tuned to allow for the existence of life, has faced several significant criticisms from the scientific community. One primary objection is that the principle may be a form of selection bias. Critics argue that we observe a universe compatible with our existence simply because we could not exist to observe it otherwise. This perspective suggests that the apparent fine-tuning is not evidence of design or purpose, but rather an inevitable consequence of our ability to observe. Another criticism targets the principle's explanatory power. Skeptics contend that the anthropic principle does not actually explain why the universe is the way it is, but merely restates the observed conditions. They argue that it fails to provide a mechanism for how these conditions came to be, essentially describing the outcome without elucidating the process. The multiverse theory also challenges the anthropic principle. This concept proposes the existence of multiple universes with varying physical constants. In this scenario, our universe's apparent fine-tuning becomes less remarkable, as it would be just one of many possible configurations. Critics argue that if infinite universes exist, one compatible with life would inevitably arise without requiring special explanation. Lastly, some scientists criticize the anthropic principle for potentially stifling scientific inquiry. They argue that accepting the universe's parameters as given because they allow for our existence might discourage the search for deeper physical explanations. This concern highlights the importance of continuing to investigate the fundamental nature of our universe rather than accepting its current state as an unexplainable given. The multiverse theory and the anthropic principle are interconnected concepts that help scientists grapple with fundamental questions about our universe and our place within it. The multiverse theory proposes that our universe is just one of many, possibly infinite, universes existing simultaneously. Each of these universes might have different physical laws, constants, and properties. The anthropic principle, on the other hand, suggests that the observable properties of our universe are compatible with the conscious life that observes it. In other words, we observe a universe that appears fine-tuned for our existence because if it were not, we would not be here to observe it. When we combine these two ideas, we arrive at a fascinating explanation for the apparent fine-tuning of our universe. Instead of requiring a single universe to be perfectly calibrated for life, the multiverse theory allows for countless universes with varying conditions. In this vast ensemble of universes, some will inevitably have the right conditions for life to emerge. This perspective shifts our understanding of our place in the cosmos. Rather than seeing our universe as uniquely designed for life, we might consider ourselves fortunate observers in one of the relatively few universes capable of supporting complex structures like galaxies, stars, and ultimately, conscious beings. This view addresses the puzzle of fine-tuning without resorting to supernatural explanations, offering a naturalistic framework for understanding our existence in a vast and varied cosmic landscape. The apparent fine-tuning of the universe is indeed a fascinating topic that has sparked much debate in scientific circles. One explanation that does not invoke a creator is the concept of the multiverse. This theory suggests that our universe is just one of many, possibly infinite, universes with different physical constants and laws. In this scenario, most universes might be inhospitable to life, but with a vast number of universes, some would inevitably have the right conditions for life to emerge. We find ourselves in such a universe not because it was designed for us, but simply because it is the only type of universe in which we could exist to observe it. This idea is known as the anthropic principle. Another perspective comes from the field of quantum mechanics. Some interpretations suggest that the universe's properties might not be as finely tuned as they appear. Instead, they could be the result of quantum fluctuations or other mechanisms we do not yet fully understand. It is important to note that while these explanations do not require a creator, they also do not disprove the existence of one. The question of fine-tuning remains an active area of research in physics and cosmology, with scientists continually developing new theories and looking for ways to test them. Observer selection bias is a crucial factor in understanding the anthropic principle. This bias arises from the fact that we, as conscious beings, can only observe and analyze a universe that allows for our existence. It suggests that our observations of the universe are inherently skewed by the conditions necessary for our presence. The anthropic principle posits that the fundamental constants and laws of our universe appear fine-tuned for life, because if they were different, we would not be here to observe them. Observer selection bias explains why we might perceive this apparent fine-tuning without necessarily implying a purposeful design. Consider the vast number of possible universes with different physical constants. Most of these hypothetical universes would likely be inhospitable to life as we know it. However, we can only find ourselves in a universe capable of supporting our existence. This bias limits our ability to assess the true probability or rarity of a life-supporting universe. Understanding observer selection bias helps us interpret cosmological observations more accurately. It reminds us to be cautious when drawing conclusions about the nature of the universe based solely on our existence within it. This concept plays a vital role in discussions about the multiverse theory and the apparent fine-tuning of cosmological constants. The anthropic principle and cosmic inflation are two fascinating concepts in cosmology that intersect in intriguing ways. Cosmic inflation theory proposes that the early universe underwent a period of rapid expansion, growing exponentially in size within a fraction of a second after the Big Bang. This process helps explain why our universe appears flat, homogeneous, and isotropic on large scales. The anthropic principle, on the other hand, suggests that the observed properties of the universe must be compatible with the conscious life that observes it. In other words, we observe a universe that allows for our existence because if it did not, we would not be here to observe it. This principle comes into play when considering the outcomes of cosmic inflation. Cosmic inflation can lead to the creation of multiple universes, each with potentially different physical constants and laws. This multiverse scenario aligns with the anthropic principle by providing a vast array of cosmic environments. In this context, our universe with its life-supporting properties becomes one of many possible outcomes. The connection between these concepts becomes particularly relevant when addressing the fine-tuning problem in physics. Many of our universe's fundamental constants appear precisely calibrated to allow for the existence of complex structures like galaxies, stars, and ultimately, life. The combination of cosmic inflation and the anthropic principle offers a potential explanation for this apparent fine-tuning without resorting to design or purpose. The anthropic principle has significant implications for our search for extraterrestrial life, challenging our understanding of our place in the cosmos. This principle suggests that the universe must have properties that allow for the development of intelligent life as we observe it. When applied to the quest for alien civilizations, it raises intriguing questions about the rarity or abundance of life beyond Earth. One interpretation of the anthropic principle implies that the conditions necessary for life might be extremely rare in the universe. This could mean that Earth is a cosmic oasis, possibly the only planet harboring complex life forms. If true, this would significantly reduce the likelihood of finding extraterrestrial intelligence, making our search more challenging and potentially fruitless. However, another perspective on the anthropic principle suggests that if the conditions for life exist on Earth, they might also exist elsewhere in the vast expanse of the universe. This view encourages the continuation of our search, as it implies that life could be more common than we initially thought. It supports the idea that given the right conditions, life might emerge and evolve on other worlds, just as it did on Earth. The anthropic principle also prompts us to consider the possibility of alternative forms of life that might exist under different conditions than those we find familiar. This expands our search parameters and challenges us to think beyond our Earth-centric views of what constitutes life. As we continue to explore the cosmos, The anthropic principle serves as both a guide and a reminder of the complex interplay between life and the universe that surrounds it. Universal laws play a crucial role in shaping our understanding of time. These fundamental principles, such as the laws of thermodynamics and relativity, provide a framework for how time behaves across the cosmos. Einstein's theory of relativity revolutionized our perception of time, revealing that it is not absolute, but relative to the observer's frame of reference. This means that time can flow at different rates depending on factors like gravity and velocity. In regions of intense gravitational fields, such as near black holes, time slows down dramatically compared to areas with weaker gravity. The second law of thermodynamics, which deals with entropy and the arrow of time, suggests that time has a direction. It explains why we experience time as moving forward, with events progressing from past to future. This law underlies the concept of cause and effect, forming the basis for our linear perception of time. Quantum mechanics further complicates our understanding of time at the smallest scales. At the quantum level, time becomes fuzzy and less well-defined, challenging our classical notions of temporal progression. These universal laws collectively shape our comprehension of time, revealing its complex and multifaceted nature across the universe. The arrow of time refers to the one-way direction in which time appears to flow from the past through the present and into the future. This concept emerges from our everyday experiences, where we observe events unfolding in a specific sequence that cannot be reversed. Interestingly, most fundamental laws of physics do not distinguish between the past and future. They work equally well in both directions. However, the arrow of time emerges from the second law of thermodynamics, which states that the total entropy or disorder of an isolated system always increases over time. This increase in entropy gives rise to the asymmetry we perceive as the arrow of time. For instance, a broken egg cannot spontaneously reassemble itself, and a cup of hot coffee left on a table will cool down rather than heat up. These everyday observations reflect the universe's tendency to move from ordered states to more disordered ones. The arrow of time is also closely linked to the expansion of the universe. As the cosmos expands, it moves from a more ordered state in the past to a less ordered state in the future, aligning with our perception of time's direction. This connection between thermodynamics, cosmology, and our everyday experience of time showcases the profound interplay between physical laws and our perception of reality. Time is a fundamental aspect of our universe, yet its true nature remains one of the most perplexing questions in physics. Many scientists and philosophers have indeed suggested that our perception of time as a flowing, linear progression might be an illusion created by our minds. Our brains process information sequentially, giving us the sensation of events occurring one after another. This cognitive framework helps us make sense of the world and navigate our daily lives. However, some theories in physics, such as special relativity, suggest that past, present, and future might all exist simultaneously in a four-dimensional block universe. Einstein's work demonstrated that time is relative and can be affected by factors like gravity and speed. This challenges our intuitive understanding of time as an absolute, universal constant. Furthermore, at the quantum level, time behaves in ways that defy our classical understanding, with particles seeming to exist in multiple states simultaneously until observed. While time as we experience it might be a construct of our perception, it is important to note that time as a dimension of the universe is very real and measurable. The debate continues among scientists and philosophers about whether our subjective experience of time reflects its true nature or if it is indeed an illusion shaped by the limitations of human cognition. Relativity theory fundamentally alters our perception of time, revealing it to be far more complex and intriguing than we once believed. In the realm of special relativity, time is not absolute but relative, changing based on an observer's motion. As objects approach the speed of light, time slows down for them compared to stationary observers. This phenomenon, known as time dilation, has been proven through precise atomic clocks on fast-moving aircraft and satellites. General relativity further expands our understanding by showing that gravity also affects the passage of time. Clocks in stronger gravitational fields tick more slowly than those in weaker fields. This means time moves differently depending on your proximity to massive objects like planets or stars. Astronauts on the International Space Station, for instance, age slightly slower than people on Earth due to both their speed and the weaker gravitational field. These relativistic effects challenge our intuitive notions of simultaneity and fixed time. Events that appear simultaneous to one observer might occur at different times for another, depending on their relative motion. This realization leads to the concept of spacetime, where time is interwoven with the three spatial dimensions, forming a four-dimensional continuum. The implications of relativity extend to our understanding of the universe itself. It allows for the possibility of time travel into the future and provides the theoretical framework for understanding phenomena like black holes, where time and space behave in ways that defy our everyday experience. Relativity has transformed time from a simple, universal constant into a dynamic and malleable aspect of our reality. The block universe theory presents a radical view of time and space, suggesting that past, present, and future exist simultaneously. This concept challenges our everyday perception of time as a flowing river, instead proposing that all moments in the universe are equally real and permanent. According to this theory, time is not a dynamic process, but a dimension similar to space. Just as we can move through space in different directions, the block universe implies that all moments in time coexist in a four-dimensional structure. This means that events we consider past or future are just as real as the present moment, merely existing at different coordinates in this time dimension. This perspective has profound implications for our understanding of reality and free will. If all moments exist concurrently, it suggests that the future is predetermined, as it already exists alongside the past and present. This idea can be unsettling, as it seems to contradict our sense of agency and ability to make choices that shape the future. The block universe theory aligns with some interpretations of Einstein's theory of relativity, which shows that the perception of time can vary depending on an observer's frame of reference. While this concept remains debated among physicists and philosophers, it continues to challenge our fundamental assumptions about the nature of time and our place within the cosmos. Quantum mechanics and general relativity present starkly different views of time, highlighting one of the fundamental challenges in modern physics. In quantum mechanics, time is treated as a background parameter, flowing uniformly and independently of the systems being studied. It serves as a framework for measuring changes in quantum states, but is not itself affected by quantum phenomena. General relativity, on the other hand, views time as an integral part of the fabric of spacetime. According to Einstein's theory, time is not absolute, but can be warped and distorted by the presence of mass and energy. This leads to effects such as time dilation, where time passes more slowly in strong gravitational fields or at high velocities. The clash between these two perspectives becomes apparent when trying to describe phenomena at both quantum and cosmic scales. Quantum mechanics struggles to account for the curvature of spacetime, while general relativity fails to incorporate the probabilistic nature of quantum events. This incompatibility has driven the search for a unified theory of quantum gravity, which would reconcile these disparate views of time. The differing treatments of time in quantum mechanics and general relativity reflect deeper philosophical questions about the nature of reality and our understanding of the universe. Resolving this conflict remains one of the most significant challenges in theoretical physics, with potential implications for our comprehension of the cosmos and the fundamental nature of existence itself. Entropy plays a crucial role in determining the direction of time, acting as a cosmic arrow that points from the past to the future. This fundamental concept in physics describes the tendency of systems to become more disordered over time. As entropy increases, it creates a clear distinction between past and future states, giving time its apparent direction. In our everyday experience, we observe countless examples of entropy at work. A cup of hot coffee cools down, but a cold cup never spontaneously heats up. Broken eggs do not reassemble themselves, and mixed paints do not separate back into their original colors. These irreversible processes are all manifestations of increasing entropy, aligning with our perception of time moving forward. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This law provides a fundamental explanation for why we experience time as unidirectional. As the universe expands and evolves, it moves from a state of lower entropy to higher entropy, creating what we perceive as the flow of time. Interestingly, at the microscopic level, many physical laws are time-symmetric, meaning they work equally well forward and backward in time. However, when we consider large systems and the statistical behavior of countless particles, the entropic increase becomes apparent, giving rise to the macroscopic arrow of time we experience in our daily lives and observe throughout the cosmos. The question of time before the Big Bang is a complex and intriguing one that challenges our understanding of the universe. In the context of our current scientific models, time as we know it began with the Big Bang. This event marks the start of our observable universe and the beginning of what we call cosmic time. However, some theoretical physicists propose ideas that suggest the possibility of time existing before the Big Bang. One such concept is the cyclic model of the universe, which posits that our universe goes through endless cycles of expansion and contraction. In this scenario, time could extend infinitely into the past, with each cycle beginning with its own Big Bang. Another perspective comes from quantum theories of gravity, which attempt to reconcile general relativity with quantum mechanics. These theories sometimes hint at the existence of a pre-Big Bang state, where time might have had different properties or behaved in ways we cannot yet comprehend. It is important to note that these ideas remain highly speculative and are not yet supported by observational evidence. The nature of time before the Big Bang, if it existed at all, remains one of the greatest mysteries in cosmology, pushing the boundaries of our scientific understanding and imagination. Causality and time are deeply intertwined in our understanding of the universe. The concept of cause and effect forms the foundation of how we perceive events unfolding around us. In our everyday experience, we observe that causes always precede their effects, creating a clear arrow of time pointing from the past to the future. This relationship between causality and time is fundamental to many scientific theories, particularly in physics. The laws of thermodynamics, for instance, describe how energy and matter behave over time, always moving from more ordered states to less ordered states. This irreversibility of certain processes reinforces our perception of time as a one-way street. However, at the quantum level, things become more complex. Some quantum phenomena appear to challenge our classical understanding of causality, suggesting that effects might sometimes precede causes, or that cause and effect might occur simultaneously. These observations have led physicists to explore new models of time and causality that go beyond our intuitive understanding. Ultimately, the relationship between causality and time remains a subject of intense scientific inquiry. As we continue to probe the nature of the universe, from the smallest quantum scales to the vast expanses of the cosmos, our understanding of this fundamental connection may evolve, potentially reshaping our conception of time itself. The nature of time as continuous or discrete is a profound question in physics. If time were discrete rather than continuous, it would fundamentally alter our understanding of the universe and require a complete overhaul of many physical theories. In a universe with discrete time, events would occur in distinct, indivisible units, much like frames in a movie. This would mean there is a smallest possible unit of time below which no shorter duration could exist. Such a concept challenges our intuitive understanding of time as a smooth, flowing entity. The implications for physics would be far-reaching. Many of our current theories, including quantum mechanics and general relativity, rely on continuous time. Equations of motion, which describe how objects move and interact, would need to be reformulated. The very notion of velocity and acceleration would have to be redefined, as these concepts typically involve continuous changes over time. Discrete time could potentially resolve some long-standing issues in physics, such as the problem of infinities in quantum field theory. However, it would also introduce new challenges, particularly in reconciling this idea with the observed smoothness of macroscopic phenomena. The search for a theory of quantum gravity, which aims to unite quantum mechanics and general relativity, might be significantly impacted by such a fundamental shift in our understanding of time. A theory of everything represents the ultimate goal in physics, a single comprehensive framework that explains all fundamental forces and particles in the universe. This ambitious concept aims to unify our understanding of the cosmos, from the tiniest subatomic particles to the largest structures in the universe. Currently, physics relies on two main theories: quantum mechanics, which describes the behavior of particles at the smallest scales, and general relativity, which explains gravity and the structure of space-time. While both theories work exceptionally well in their respective domains, they are incompatible with each other. A theory of everything would bridge this gap, providing a unified explanation for all physical phenomena. Such a theory would need to account for the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. It would also need to explain the properties and interactions of all known particles, as well as potentially predict the existence of new particles or phenomena. Despite decades of effort by brilliant physicists, a complete theory of everything remains elusive. The search continues, driving research in areas such as string theory and quantum gravity as scientists strive to unlock the deepest secrets of our universe. Unifying quantum mechanics and general relativity has been a monumental challenge for physicists for nearly a century. These two fundamental theories describe the universe at vastly different scales, and their underlying principles seem to be in conflict. Quantum mechanics governs the behavior of particles at the smallest scales, where probability and uncertainty reign supreme. It describes a world where particles can exist in multiple states simultaneously and interact instantaneously across vast distances. General relativity, on the other hand, explains gravity and the large-scale structure of the universe. It portrays space and time as a smooth, continuous fabric that can be warped by massive objects. The difficulty arises when we try to apply quantum principles to gravity or general relativity to quantum systems. In the quantum world, forces are mediated by particles, but attempts to describe gravity in this way lead to mathematical infinities and nonsensical results. Similarly, the probabilistic nature of quantum mechanics clashes with the deterministic framework of general relativity. Furthermore, the two theories have very different notions of time and space. Quantum mechanics treats time as a fixed background, while in general relativity, time is a flexible dimension that can be stretched and compressed. Reconciling these disparate views of reality has proven to be an enormous intellectual challenge, requiring new mathematical frameworks and potentially a complete reimagining of our understanding of space, time, and the fundamental nature of the universe. The quest for a theory of everything has long been a central goal in theoretical physics. Several major approaches have emerged as leading contenders in this pursuit. String theory stands out as one of the most prominent candidates. This framework proposes that all matter and forces in the universe are composed of tiny vibrating strings, existing in multiple dimensions beyond the four we can observe. String theory aims to unify quantum mechanics and general relativity, offering a potential explanation for all fundamental particles and forces. Loop quantum gravity presents another compelling approach. This theory suggests that space itself is composed of discrete units, much like the pixels on a digital screen. It attempts to reconcile quantum mechanics with general relativity by quantizing space-time itself, potentially offering insights into the nature of black holes and the early universe. Causal set theory takes a different tack, proposing that space-time is fundamentally discrete and composed of elementary events connected by causal relationships. This approach seeks to address some of the infinities that plague other theories and offers a new perspective on the nature of time and causality in the universe. Twistor theory, developed by Roger Penrose, represents yet another avenue. It reimagines space-time in terms of more fundamental geometric objects called twistors. This mathematical framework aims to unify quantum theory and gravity by recasting space-time in a form more compatible with quantum principles. While these theories each offer unique insights, the search for a definitive theory of everything continues to challenge and inspire physicists worldwide. String theory proposes a revolutionary approach to understanding the universe at its most fundamental level. It suggests that the basic building blocks of reality are not point-like particles, but incredibly tiny, vibrating strings of energy. These strings, far smaller than an atom, vibrate in different ways to create all the particles and forces we observe in nature. The key to string theory's unification lies in its ability to describe both matter and forces within a single framework. In this model, different vibrations of these strings correspond to different particles, including those that carry fundamental forces. Gravity, electromagnetism, and the strong and weak nuclear forces are all thought to arise from specific vibrational patterns of these strings. One of the most intriguing aspects of string theory is its requirement for extra dimensions beyond the four we experience in everyday life. These additional dimensions, while invisible to us, provide the necessary mathematical space for strings to vibrate in ways that could explain all known particles and forces. This multidimensional approach allows string theory to potentially reconcile the seemingly incompatible theories of general relativity and quantum mechanics. However, it is important to note that string theory remains a work in progress. While it offers an elegant theoretical solution to unifying fundamental forces, scientists have yet to find experimental evidence to support its predictions. The search for this evidence continues, driving physicists to explore new ways of testing the theory and pushing the boundaries of our understanding of the universe. Loop quantum gravity is a theoretical approach to quantum gravity that attempts to merge quantum mechanics with Einstein's theory of general relativity. It proposes that space itself is composed of tiny, discrete units called loops or spin networks, rather than being a smooth, continuous fabric. These loops are interconnected, forming a complex network that represents the structure of space-time at the quantum level. Unlike string theory, which posits that all matter and forces are composed of tiny vibrating strings, loop quantum gravity focuses solely on quantizing gravity and does not attempt to unify all fundamental forces. It maintains Einstein's view of gravity as the curvature of spacetime, but suggests that this curvature is quantized at the smallest scales. Another key difference is that loop quantum gravity does not require extra dimensions to work mathematically, whereas string theory typically needs 10 or 11 dimensions. Loop quantum gravity also preserves many aspects of general relativity, including the notion of background independence, which means that space and time emerge from more fundamental quantum structures rather than existing as a fixed backdrop. While both theories aim to reconcile quantum mechanics and gravity, they take fundamentally different approaches. String theory has gained more attention and resources in the scientific community, but loop quantum gravity continues to be developed as a promising alternative in the quest for a theory of quantum gravity. Discovering a theory of everything would revolutionize our understanding of the universe. This unified theory would explain all fundamental forces and particles, bridging the gap between quantum mechanics and general relativity. It would provide a complete description of how the cosmos operates at all scales, from the tiniest subatomic particles to the largest structures in the universe. Such a breakthrough would have profound implications for physics and cosmology. Scientists could finally explain the nature of dark matter and dark energy, solving some of the most perplexing mysteries in modern astronomy. The origin of the universe and its ultimate fate might become clearer, offering insights into the Big Bang and the possibility of a multiverse. Beyond theoretical physics, a theory of everything could lead to technological advancements we can scarcely imagine. Our deeper understanding of fundamental forces could pave the way for new energy sources, revolutionary propulsion systems, or even manipulation of gravity and space-time. These developments could transform space exploration, enabling interstellar travel or the creation of artificial gravity. The philosophical and cultural impact would be equally significant. A complete understanding of the universe's workings might reshape our view of reality and our place within it. It could influence fields ranging from philosophy to theology, potentially altering how we perceive existence itself and sparking new debates about determinism, free will, and the nature of consciousness. The search for a theory of everything, often referred to as a TOE, is deeply intertwined with our quest to understand the origin of universal laws. This ambitious scientific endeavor aims to unify all fundamental forces and particles in the universe under a single, coherent framework. By pursuing this grand unification, scientists hope to uncover the underlying principles that govern the cosmos and shed light on how the laws of physics came to be. At its core, the search for a theory of everything seeks to explain why the universe behaves the way it does. It attempts to answer fundamental questions about the nature of reality, such as why certain particles exist and why forces interact in specific ways. This pursuit is driven by the belief that there must be a set of foundational rules from which all other physical laws emerge. The connection between a theory of everything and the origin of universal laws lies in the potential for such a theory to reveal the ultimate source of these laws. If successful, it could demonstrate how the seemingly diverse rules governing different aspects of the universe are actually manifestations of a more fundamental principle. This would not only provide a deeper understanding of the cosmos, but also offer insights into why these laws exist in the first place. As scientists continue their work on developing a theory of everything, they are essentially trying to peel back the layers of reality to uncover the most basic building blocks and rules of the universe. This ongoing search may ultimately lead us to the very foundations of existence, potentially revealing the origin and nature of the universal laws that shape our reality. A theory of everything represents the ultimate goal in physics, aiming to unify all fundamental forces and particles in a single, coherent framework. This grand unified theory could potentially shed light on the origin of the universe, offering unprecedented insights into the moments following the Big Bang. By combining quantum mechanics and general relativity, a theory of everything might explain how the universe emerged from a singularity, a point of infinite density and temperature. It could reveal the nature of the primordial energy that expanded into our cosmos and elucidate the processes that led to the formation of matter and the large-scale structures we observe today. Such a theory might also address fundamental questions about the nature of space and time, potentially explaining why our universe has the specific properties and physical constants we observe. It could provide a deeper understanding of concepts like dark energy and dark matter, which play crucial roles in cosmic evolution but remain poorly understood. However, developing a theory of everything presents enormous challenges. Despite decades of research, physicists have yet to formulate a complete and testable unified theory. While string theory and loop quantum gravity offer promising avenues, a comprehensive explanation of the universe's origin remains one of the most profound and elusive goals in science. Current attempts at a theory of everything face several significant challenges. One major criticism is the lack of experimental evidence to support these theories. Many proposed frameworks, such as string theory, operate at energy scales far beyond our current technological capabilities to test, making it difficult to verify or falsify their predictions. Another issue is the mathematical complexity of these theories. Some critics argue that the intricate mathematical structures used in theories like loop quantum gravity are so abstract that they may not correspond to physical reality. This complexity also makes it challenging for the broader scientific community to fully engage with and evaluate these ideas. The inability to reconcile quantum mechanics with general relativity remains a persistent problem. While various approaches attempt to bridge this gap, none have yet provided a fully satisfactory solution that can explain both the quantum world and the large-scale structure of the universe in a unified framework. Lastly, some scientists question whether a theory of everything is even possible or necessary. They argue that different scales of the universe might be governed by fundamentally different principles, and seeking a single overarching theory could be misguided. This philosophical debate about the nature of scientific understanding adds another layer of complexity to the ongoing quest for a unified theory of physics. The discovery of a theory of everything, often called a TOE, would revolutionize our understanding of reality and potentially shed new light on the nature of consciousness. This unified theory would combine all fundamental forces and particles in physics, offering a complete explanation of how the universe works at its most basic level. Such a breakthrough could provide insights into the fabric of space-time and the origins of the universe, potentially revealing hidden dimensions or parallel realities. This deeper understanding of the cosmos might help us grasp how consciousness emerges from the physical world, bridging the gap between mind and matter. A theory of everything could also unveil new principles governing information and complexity, which are crucial to understanding consciousness. It might reveal how the brain's neural networks give rise to our subjective experiences, emotions, and thoughts. This could lead to advancements in artificial intelligence and our ability to replicate or enhance consciousness. Furthermore, a TOE might challenge our current notions of reality, suggesting that consciousness itself plays a fundamental role in shaping the universe. This could blur the lines between observer and observed, leading to profound philosophical implications about the nature of existence and our place within it. Symmetry in physics is a fundamental concept that underpins many of our most important theories about the universe. It refers to the idea that certain aspects of a system remain unchanged when we perform specific transformations or operations on that system. This principle extends far beyond the simple geometric symmetry we might observe in everyday objects. In the realm of particle physics, symmetries play a crucial role in understanding the behavior of subatomic particles and the forces that govern their interactions. For instance, the concept of charge symmetry suggests that if we were to swap all particles with their antiparticles, the laws of physics would remain the same. This symmetry helps explain the existence of antimatter and provides insights into the early moments of the universe. Symmetries also manifest in the conservation laws that are cornerstones of physics. The conservation of energy, for example, arises from the symmetry of time translation, meaning that the laws of physics remain constant regardless of when an experiment is performed. Similarly, the conservation of momentum is linked to the symmetry of space translation, indicating that the laws of physics are the same everywhere in the universe. Perhaps most intriguingly, symmetries can be broken, leading to some of the most profound revelations in modern physics. The breaking of symmetry between matter and antimatter in the early universe, for instance, is believed to be responsible for the predominance of matter we observe today. This concept of symmetry breaking continues to drive research in particle physics and cosmology, offering tantalizing clues about the nature of our universe and its fundamental laws. Symmetry and conservation laws are deeply interconnected in physics, forming a fundamental relationship that underpins our understanding of the universe. This connection was first recognized by Emmy Noether, a brilliant mathematician who formulated what is now known as Noether's theorem. At its core, Noether's theorem states that for every symmetry in nature, there is a corresponding conservation law. In simpler terms, when a system remains unchanged under certain transformations, we can identify a quantity that stays constant throughout those changes. This principle applies across various scales, from subatomic particles to cosmic structures. For instance, the conservation of energy stems from the symmetry of time translation. This means that the laws of physics remain the same regardless of when an experiment is performed. Similarly, the conservation of momentum arises from the symmetry of space translation, indicating that the laws of physics are the same everywhere in space. These symmetry-based conservation laws provide powerful tools for physicists to understand and predict the behavior of physical systems. They allow us to make sense of complex phenomena and uncover the underlying order in the apparent chaos of the universe. By recognizing these symmetries, scientists can simplify complex problems and gain deeper insights into the fundamental workings of nature. Symmetry breaking in the early universe played a crucial role in shaping the cosmos we observe today. In the first moments after the Big Bang, the universe existed in a state of perfect symmetry, with all fundamental forces unified into a single, immensely powerful force. As the universe expanded and cooled, this symmetry began to break down, leading to the separation of the four fundamental forces we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This process of symmetry breaking had profound consequences for the formation of matter and the structure of the universe. It allowed for the creation of distinct particles, such as quarks and electrons, which form the building blocks of atoms. Without symmetry breaking, these particles would not have acquired their unique properties, and matter as we know it could not have formed. Furthermore, symmetry breaking is believed to have caused the slight imbalance between matter and antimatter in the early universe. This imbalance was crucial for our existence, as it allowed matter to survive the annihilation process with antimatter, leaving behind the matter that makes up our universe today. The concept of symmetry breaking also extends to the formation of large-scale structures in the universe. It is thought to have played a role in the creation of cosmic inflation, a period of rapid expansion in the early universe that led to the formation of galaxies and galaxy clusters. By understanding symmetry breaking, scientists gain valuable insights into the fundamental nature of our universe and its evolution from the earliest moments to the present day. Supersymmetry represents a bold attempt to expand our comprehension of the fundamental building blocks of the universe. This theoretical framework proposes that every known particle has a hidden counterpart, effectively doubling the cast of characters in the cosmic drama of particle physics. At its core, supersymmetry suggests a profound connection between two types of particles: fermions, which make up matter, and bosons, which carry forces. According to this theory, each fermion would have a corresponding boson partner and vice versa. For instance, the electron would be paired with a particle called the selectron, while the photon would have a partner known as the photino. This symmetry between matter particles and force carriers could potentially solve several puzzling issues in particle physics. One of the most intriguing possibilities is that supersymmetry might explain the nature of dark matter, the mysterious substance that appears to hold galaxies together. Some supersymmetric particles, if they exist, could be candidates for dark matter particles. Moreover, supersymmetry could help unify the fundamental forces of nature at high energies, bringing us closer to the long-sought goal of a theory of everything. It might also address the hierarchy problem in particle physics, explaining why the Higgs boson is much lighter than theoretical calculations suggest it should be. Despite its elegance and potential, supersymmetric particles have yet to be detected, leaving physicists eager to uncover evidence of this captivating theory. Symmetry plays a fundamental role in the standard model of particle physics, serving as a guiding principle for understanding the behavior of fundamental particles and forces. At its core, the standard model is built upon the concept of symmetries in nature, which help explain how particles interact and transform. In the Standard Model, symmetries are not just aesthetic features, but powerful tools that predict the existence of particles and dictate the laws of their interactions. These symmetries are mathematical in nature and describe how physical systems remain unchanged under certain transformations. For instance, the symmetry known as gauge invariance is crucial in describing the electromagnetic, weak, and strong nuclear forces. One of the most important symmetries in the Standard Model is called gauge symmetry. This principle allows physicists to derive the existence of force-carrying particles, such as photons for electromagnetism and gluons for the strong nuclear force. Without these symmetries, our understanding of particle interactions would be incomplete and inconsistent. However, nature also exhibits instances of symmetry breaking, which are equally important in the Standard Model. The most famous example is the Higgs mechanism, which explains how particles acquire mass. This symmetry-breaking process is essential for creating the diverse range of particle masses we observe in the universe, from the lightweight electron to the hefty top quark. Symmetry plays a crucial role in guiding the search for new physical theories, serving as a powerful tool for scientists to unravel the fundamental laws of nature. At its core, symmetry in physics refers to the idea that certain aspects of a system remain unchanged under specific transformations. This concept has proven invaluable in predicting and describing the behavior of particles and forces in the universe. One of the most striking examples of symmetry's importance is in particle physics. The Standard Model, our current best understanding of fundamental particles and forces, is built upon symmetry principles. These symmetries have led to the prediction and subsequent discovery of numerous particles, including the Higgs boson. Scientists use symmetry as a guiding principle to construct mathematical models that describe the universe, often revealing new particles or interactions before they are experimentally observed. Symmetry also helps simplify complex problems in physics. By identifying the symmetries present in a system, researchers can reduce the number of variables they need to consider, making seemingly intractable problems solvable. This approach has been particularly fruitful in areas such as quantum field theory and string theory, where symmetry considerations have led to profound insights into the nature of space, time, and matter. Furthermore, symmetry breaking has proven to be just as important as symmetry itself. The universe we observe today is full of asymmetries, from the dominance of matter over antimatter to the distinct properties of different fundamental forces. Understanding how and why these symmetries break down at certain energy scales or conditions has become a central focus in the development of new physical theories, potentially holding the key to explaining some of the most perplexing mysteries in modern physics. Symmetry and the laws of thermodynamics share a profound connection in the realm of physics. This relationship stems from a fundamental principle known as Noether's theorem, which states that every symmetry in nature corresponds to a conserved quantity. The laws of thermodynamics, particularly the first law, deal with the conservation of energy. This conservation principle is closely tied to the symmetry of time translation, meaning that the laws of physics remain the same regardless of when an experiment is performed. This temporal symmetry ensures that energy is conserved across all physical processes. The second law of thermodynamics, which introduces the concept of entropy, is related to the breaking of time reversal symmetry. While most fundamental laws of physics are time-symmetric, the second law introduces an arrow of time, dictating that entropy always increases in closed systems. This asymmetry in time reflects the irreversible nature of many thermodynamic processes. Furthermore, the third law of thermodynamics, which deals with the behavior of systems as they approach absolute zero temperature, relates to the symmetry of matter at extremely low energies. As temperatures decrease, many materials exhibit increased order and symmetry in their atomic structures, aligning with the principles of quantum mechanics and statistical physics. Symmetry in physics and mathematics are deeply interconnected, with mathematical symmetry serving as a powerful tool for understanding and describing physical phenomena. In physics, symmetry refers to the idea that certain aspects of a system remain unchanged under specific transformations. This concept mirrors the mathematical notion of symmetry, where an object or equation maintains its properties when subjected to particular operations. One of the most fundamental examples of this relationship is found in the laws of conservation. The conservation of energy, for instance, is directly linked to the symmetry of time translation. This means that the laws of physics remain the same regardless of when an experiment is performed. Similarly, the conservation of momentum is tied to the symmetry of space translation, indicating that the laws of physics are the same everywhere in space. These symmetries in physics are often expressed and analyzed using mathematical group theory. Groups, which are mathematical structures that describe symmetries, allow physicists to classify and understand the fundamental forces and particles in the universe. The standard model of particle physics, our current best understanding of the subatomic world, is built upon the symmetries described by specific mathematical groups. Moreover, symmetry principles have guided physicists in formulating new theories and making predictions. The concept of supersymmetry, for example, proposes a fundamental symmetry between fermions and bosons, potentially unifying our understanding of matter and force particles. While not yet experimentally confirmed, this theory demonstrates how mathematical symmetry concepts continue to drive advances in theoretical physics. Asymmetry indeed plays a crucial role in the emergence of complexity in the universe. This fundamental concept underlies many of the structures and phenomena we observe, from the smallest subatomic particles to the largest cosmic scales. At the most basic level, the slight imbalance between matter and antimatter in the early universe allowed for the existence of the matter-dominated cosmos we see today. Without this asymmetry, matter and antimatter would have annihilated each other completely, leaving nothing but energy. On larger scales, asymmetry drives the formation of galaxies and cosmic structures. Tiny fluctuations in the density of the early universe, believed to be quantum in origin, led to areas of slightly higher and lower density. These asymmetries grew over time due to gravity, eventually forming the cosmic web of galaxies and voids we observe. Even life itself relies on asymmetry. Many biological molecules, such as amino acids and sugars, exist in specific chiral forms, meaning they have a distinct handedness. This molecular asymmetry is crucial for the function of proteins and the storage of genetic information, allowing for the complexity of living organisms. Symmetry plays a crucial role in the quest for a theory of everything, serving as a guiding principle for physicists as they attempt to unify all fundamental forces and particles in the universe. At its core, symmetry in physics refers to the idea that certain aspects of nature remain unchanged under specific transformations. This concept has proven invaluable in understanding the fundamental laws that govern our universe. The search for a theory of everything aims to reconcile quantum mechanics, which describes the behavior of particles at the smallest scales, with general relativity, which explains gravity and the structure of spacetime. Symmetry provides a powerful framework for this unification, as it has already been successfully applied in both quantum field theory and particle physics. One of the most significant applications of symmetry in this pursuit is the concept of supersymmetry, which proposes a fundamental relationship between fermions and bosons, the two types of particles that make up all matter and forces. Supersymmetry suggests that every known particle has a yet undiscovered partner with different properties, potentially explaining some of the mysteries in particle physics and offering a path towards unification. Furthermore, symmetry considerations have led to the development of string theory and its extensions, which propose that all particles and forces are manifestations of tiny vibrating strings in multiple dimensions. These theories rely heavily on complex symmetries to describe the fundamental nature of reality, bringing us closer to a comprehensive understanding of the universe and potentially uncovering the elusive theory of everything.